So I think we can start. Good morning, welcome all. So this is the 9th edition of this optimal transport meeting we initiated with Giuseppe Buttazzo in 2001. So now quite many years elapsed from that time. Many new mathematical things happened, and you can see also from the list of speakers and topics, and also for the participation to this meeting, that this is still a very active research area, and I hope you will enjoy this meeting. I have just a quick, a short announcement, then the agenda is very tight, so we should start immediately. And I am organizing in January, I don't know if it is possible to display it. Yeah, okay, that's better. Okay, I am organizing in January a meeting here at the Scuola to celebrate Alessio and his field medal. And so if you're interested to attend, also the optimal transport community will be represented very well by, for instance, by Robert McCann, by José Antonio Carrillo, by Cédric Villani. And so if you're interested to attend, please register, because we need to know really the number of participants to estimate it. And the deadline for registration in the end of this month. Okay, so I think we can start, and we will move immediately to the first lecture. It's a pleasure to introduce Yann Brenier. He will be talking about the solution of the initial value problem for parabolic systems by convex minimization. Thank you.
Okay. So, yes, I have the microphone, so is it okay? The sound is okay? And how do we... Oh, yes. Okay, so how do we... So does it work? Okay, because this is yes, and so I will be. Okay, so and so let me see. Yes. Oh yeah, very good. Okay, so thank you for the invitation. It's a pleasure for being here, at least for this 9th edition. You said, yeah. And probably I was in all of them so far. So I hope this will continue this way. And so I am going to talk about a problem of solving by initial value problems by convex minimization techniques, and I will focus on the parabolic case. Although I started this study about now 1 year and a half ago. And 1 year ago, actually, and I started really with a hyperbolic equation. So at the end, I will give a little bit of information about hyperbolic equation. But in order to present a more recent result, I will start with the parabolic case. Okay, so the idea of solving initial value problems by convex minimization is very old. And for linear equation, this is the so-called least square method. And for nonlinear equation, this is much more challenging, because for linear equation, you just square the equation, and you try to minimize the square. And since it's convex, and you expect the minimum to be 0. So it's pretty stupid. However, if you do that in the nonlinear setting, then of course, very likely the square of the nonlinear equation will not be convex. So this is used for instance in some practical application if you do some data assimilation for weather forecasting. So you may use this kind of methods anyway. But of course, you have to face the problem of local minima. And this is not so nice. However, there has been some attempt to do to try the nonlinear setting. So there is a very famous paper by Brenier, and this was followed by Nassif Ghoussoub, and also there is Milko, and I'm certainly forgetting a lot of people in this list. Sorry about that. And so I think the method I'm going to introduce is of different nature. Okay, so maybe there are some equivalents, but so far I didn't see really the equivalence. And in a recent work, which will be published soon, we have addressed first the case of systems of hyperbolic conservation law with a convex entropy. I started with this, and so which includes the famous Euler equation of compressible fluid mechanics as a special example, but also a baby problem, which is the Burger's equation. And for the Burger's equation, in some sense, I got a fully satisfactory result that you can use this method globally in time. That is, for every time interval, you can recover the correct entropy solution by a convex minimization technique. However, for more complicated problem like the Euler equation, this is only a local techniques. So you get for smooth solution, you can recover smooth solution of the initial value problem for small time, and for large time it is unclear what you get, and it is related to the concept of sub-solution in the theory of convex integration, typically. Okay, oh, there is something funny. Yeah. And so let me start with a very simple example that I just worked out a few weeks ago. Actually, this was during at the occasion of the meeting for Alex Milke. So since I had given a similar talk in front of him, I had to do something new. So I decided to give an example in the parabolic setting. It turns out that the parabolic setting works pretty well, at least in this very simple example of the post-medium equation. So what I'm going to say works for any power in the post-medium equation, but of course, to simplify notation, I just take the quadratic one, where the power is 2. But what I'm going to say, it works for any power of u, as long as the power is larger than 1. So this is really the post-medium equation, and it is exactly the same story. However, the notation are much simpler with u squared. Okay, so this is the equation. You are dealing with non-negative solutions. And the basic idea is completely silly. So maybe this probably is new because of the silliness of the first idea. Okay, so the idea, you want to solve the initial value problem by minimizing something subject to be a solution of the evolution equation. So which is completely crazy. Okay, especially in the parabolic setting where very likely you get uniqueness results. So this is completely absurd. So what I'm going to minimize is the time integral of the so-called entropy. So there is a concept of entropy for the post-medium equation, which is very well known in this community, in particular due to the famous work of Felix Otto for the post-medium equation, and then where the post-medium equation has been interpreted as the gradient flow of some entropy function for the optimal transportation metric. And in that case, for the square, the entropy is just the square. The square of the function, and here I am minimizing the time integral of the entropy. Okay, and the subject to be for you to be a weak solution of the post-medium equation with a given initial condition. So in the weak formulation, I also include the initial condition. So in some sense, this is absurd because typically for this rather simple parabolic equation, we get nice uniqueness results. So this is really an absurd problem. In the hyperbolic setting, is less silly because of convex integration technique shows that you can produce a lot of crazy weak solution for given initial condition. So in the hyperbolic setting, this is not so absurd. In the parabolic setting, it looks really silly. Okay, so now we can write that as a saddle point problem by including the weak formulation in the supremum. So I minimize in U, and I do a supremum with respect to phi, where phi is a test function. So if you look at the supremum in phi, everything is linear in phi. So this supremum is either plus infinity. Okay, if you put away the u square, if you all the terms that we maximize in phi gives either plus infinity or 0, and you get plus infinity unless u is a weak solution of the porous medium equation, including the initial condition U0. So I wrote the initial condition is in a slightly unusual way as 2U. Well, the 2 is cosmetic. It's just okay. So U0 dt phi. Remember that U0 depends only on x. So when I integrate space-time U0 dt phi, I get U0 phi of capital T minus phi of 0, and I will assume that phi vanishes at capital T. So in this way, I encode the initial condition in the usual way. So this is really a way of encoding the initial value problem in the weak formulation. And so the test function phi should vanish at the final time. It's very important because we don't want to use any information about the future. We are just using information at the initial time. And I mean, just to make sense, you see that it's enough to get a square integrable function in Q. Okay, so now something which is more interesting is to look at the relaxed problem, which is obtained by exchanging the infimum and the supremum. And I claim that this problem is of interest. The first one is silly, but the second one is more interesting. And you see that since I perform the infimum first in U, the functional in phi is automatically concave. Because you see everything is linear in phi. So when I perform any kind of infimum in U, I will get a concave functional of dt phi and Laplacian of phi. So in some sense, in order to get convexity, I use this very simple idea that a weak formulation is always linear with respect to the test function. Okay. So I mean, the weak formulation, everybody knows now that the weak formulation is very terrible in many problems like Euler, because of the lack of uniqueness, but sometimes it's useful, and typically for minimization purpose it's good to have this linearity with respect to the test function. Okay, so now it's very easy to compute this J because you see that there is no derivative of U involved in the formulation. This is due to the structure of the porous medium equation, because we have a good separation between differential operator and nonlinearity. So in some sense we get only local term in U, and therefore because of the positivity of the integral, we can do the minimization point by point in a very easy way. And since we have squared, it's not very hard to do. And so let me rewrite the formula, and you see that since we have something quadratic in U, so there is only two possibilities. Either the coefficient in front of U square is non-negative, that is 1 minus Laplacian of phi is non-negative, and in this case you get a nice infimum that you can compute explicitly. For instance, you just take the optimal value of U, and so the optimal value of U should satisfy U minus dt phi minus grad phi U is 0. So which means that you have a very simple expression of U in terms of dt phi. So U is just dt phi divided by 1 minus Laplacian of phi. And therefore, when I compute everything, this is what I get. I get the supremum in phi of minus dt phi squared divided by 1 minus Laplacian of phi plus a linear term. Of course, this makes sense only if Laplacian of phi is less than 1. And I remind you that we still enforce the final condition for phi, that phi should be 0 at capital T. So of course, this is a little bit ambiguous because 1 minus Laplacian of phi might vanish, but anyway, if you look at the problem in a slightly different way by introducing, giving a name to the time derivative, let's call it Q, and let's give a name to 1 minus Laplacian of phi, let's call it sigma, then we can rewrite the whole thing as minus Q squared divided by sigma plus 2U0Q, subject to, of course, sigma and Q are related by a compatibility condition because they are derivative, and the compatibility condition is that the time derivative of sigma plus the Laplacian of Q should be 0. And of course, now the final condition is on sigma, and since sigma is 1 minus Laplacian of phi, sigma of capital T should be 1. So and you see that this problem is very much like an optimal transportation problem, and I would say it is even more like the ballistic version of the optimal transport problem, if I'm not mistaken. So I don't know if Nassif has already arrived. Is he here, or it's on the way to? Oh yes. So would you? I don't know if okay. It looks to me, because I didn't read very carefully Nassif paper, so it looks to me like this should be like a ballistic version of the optimal transport problem. You can also see that this is kind of very elementary mean field games in some sense, because typically you don't put an initial condition for sigma. So there is no initial conditions for sigma. There is an initial condition for the velocity in some sense. So u0 is like the direction of the shooting. So it's really a kind of ballistic problem. So you see that, and therefore now we don't care so much about 1 minus Laplacian of phi, because we are used to this functional q squared divided by sigma, and we know that it's perfectly fine convex function, of course, which takes value plus infinity as soon as sigma is strictly negative, or also as sigma is 0 and q is not 0. So this function is like a barrier, a natural barrier function to enforce the constraint that that 1 is larger than the Laplacian of phi. Okay, so it looks like a very nice problem, and however we can do even better, because, and this is something that I discovered, so it's very elementary, but it is very much related to this famous bounds that actually I had completely forgotten for years, which is this Aronson-Benillan estimates, which is very much the same estimate that you get in the Burgers equation, by the way. So, which tells you that there is an unconditional bound for the Laplacian of the solution of the porous medium equation. That is, the Laplacian of u is always bounded from below by minus kappa divided by t, and kappa depends only on the dimension. So I forgot exactly the formula. It's something like d divided by d plus 2, where d is the dimension. So it's a universal bound for any type of solution. So you don't need smoothness to establish that. And this is a comparison principle with the so-called Barenblatt profile. I mean, a special self-similar solution of the porous medium equation that you can consider as like the elementary solution of this nonlinear equation, because it's formally what you would get by starting from a delta or something like that. And then there is this nice comparison principle that gives you this bound. So now I would like to show that actually going back. Sorry. Let me. Sorry. No, yeah. I'm not used to. Oh, I did. And this I don't know how to fix it. So sorry. But can I use? I mean, I prefer to use. Sure. Yes. But can I use this one? Yeah. Very good, because it's much better for me. I'm from I'm not from the 19th century, but from the 20th century. Yeah. I was born shortly after World War I. Okay. So let me go back. Okay. So now you know what I want. I would like to know. I would like to solve explicitly actually this maximization problem by finding the right phi. And it turns out that it's pretty obvious what should be phi, because we know that by minimizing in u, we got already the relationship between u and phi that I already said, that u should be like dt phi divided by 1 minus Laplacian of phi. And you see that this is like a linear equation connecting phi and u, because this is the same as dt phi is equal to u times 1 minus Laplacian of phi. So if we already have a solution to the porous medium equation, and we know that the theory of porous medium equation is pretty nice, so we have all kind of solution for this equation, and in particular in the very interesting case where u0 is strictly positive, then we know that the solution is smooth. The problem comes from the possible vanishing of the initial condition. But let's assume, for simplicity, that u0 is strictly positive, therefore u is completely smooth. And then it is tempting to solve this equation, which is a kind of parabolic equation in phi with a final, so it's a final VP, so a final value problem, where the value of phi, so it's kind of a adjoint equation is 0, and I would like to solve this equation. So of course the vanishing of u might be a problem, and actually it's even better to solve not for phi but for alpha, which is 1 minus Laplacian of phi, the quantity that we would like to estimate from below, to show that it is really better than at least non-negative and possibly strictly positive. So if you look at the equation for alpha, you just take the previous equation, you take the Laplace operator on it, and then you get that dt of alpha should be the Laplacian of alpha u. So it's very simple, right? I hope you... And the final condition for alpha is, of course, that alpha at time t should be 1, because phi at time t is 0. So this is this parabolic equation, which is a little bit unusual because you have the Laplacian in front of this equation. So I'm not completely sure about what is exactly known about this kind of linear parabolic equation in alpha. Sorry about... I am not really an expert in any sense in parabolic equation. But what I claim is from the Aronson-Benillan estimates, we deduce immediately that alpha should be bounded from below by t divided by capital T to the kappa. So the only degeneracy for alpha is time t0. So it means for any positive time, this alpha is unconditionally bounded away from 0. And since I didn't use the smoothness of u, although it is not really written up completely, so it's pretty clear that this should works for any reasonable solution to the porous medium equation. So there is only at the final time that there is a possible blow up, which makes sense because the Aronson-Benillan estimate is compatible with very, very, very crazy initial condition. So let me show you that. So it's a very elementary calculation which is fully justified if you assume u to be smooth. For generalized solution, this has to be worked out. I don't claim that it is already done. So when I expand, of course, the equation in alpha, I get 3 terms including with 2 Laplacian, Laplacian of alpha and Laplacian of u. And now if I put myself at a point in x where the infimum of alpha is reached, okay, then of course at such a point the gradient of alpha should be 0 and the Laplacian of alpha should be positive because it's a minimum, and therefore I can use the Aronson-Benillan estimates for Laplacian of u, because I know that the Laplacian of u for sure is larger than minus kappa over t. So then if you define capital A of t to be the infimum, you see that the time derivative of the infimum should be smaller than kappa A of t divided by t, because once again you get that the A prime of t should be equal to should be less than the u Laplacian of alpha at this point, which is minus u, which is negative, and you get minus alpha Laplacian of u. And because of the, well, of course you have to assume that alpha is already positive, but of course this makes sense, this is clear. But and then you can use the lower bound on minus Laplacian of u, which give an upper bound for minus Laplacian of u. So we get this estimate, and of course that everybody we can easily integrate that, and so you get the logarithm of A of t minus, okay, that's clear. And since A of capital T is 1, the logarithm of capital A of t is 0, and then we get this lower bound. So it fits perfectly well with the Aronson-Benillan estimate, and I don't fully understand why, but maybe there is a simple explanation. So of course it's not perfect because there is this lower bound vanishes at time 0. So this is the end of the proof, at least in the case where u is smooth, which is true when typically you start with a strictly positive initial condition. So in the general case, this has to be proven in a rigorous way, which certainly needs some additional effort. Okay, so now once we have that, let me check that the phi that I obtained by integrating the linear equation is really optimal. So that's a very elementary calculation. So this is the thing that I want to show to be optimal, This is the functional I want to maximize in the concave formulation of the initial value problem. And because U is a solution, and here we just use the weak formulation. We don't need to be a strong solution. So by definition of the weak formulation, we get this second integral to be 0, because this encodes that you solve the porous medium equation with initial condition U0. So which means that in the first line, the term involving U0 can be easily expressed in terms of dt phi and Laplacian of phi. Okay? And when we reorganize the terms, using that dt phi by definition is a solution of dt phi is 1 minus Laplacian phi u, and then this combines exactly to give the integral of u squared, which is the entropy of the solution integrated in time. And now we are done, because look, remember the definition of J. J is certainly below the maximum that we can get, which was capital J of U0. Okay, now U square, the integral of U square, even if by bad luck there would be a lot of weak solution, this would be still larger than the infimum of the entropy among all weak solutions, which was capital I of U0. But capital of I U0 is in inf sup, so it's always larger than the sup inf. So we get everything in the right order. So we get that J of U0, which is an upper bound for J, is larger than the entropy of U, which is larger than the optimal entropy, which is larger than J. So then all these numbers are equal, which means that phi is optimal. So in some sense, I found an explicit solution of the minimization problem, of the maximization problem, at least in the case where U is smooth. So the general situation should be worked out. I didn't do it yet, because it's too, I mean, the the meeting in Berlin is too recent, so I didn't write everything yet. So okay. So in some sense, in this framework, it turns out that the porous medium equation is now the simplest example of all this strategy I found, because even simpler than Burger's, it's the simplest example. Okay, and so once again, if you do that for the more general porous medium equation, you would get exactly the same story, using the corresponding Aronson-Benillan estimates, which is for the Laplacian of the U to the right power. Okay, so it would be exactly the same thing. So now I try to see in the dictionary of horrible parabolic equation, and then I remember the quantum diffusion equation that I think at least I don't know probably many people have worked on that, but I remember the paper by in particular by Giuseppe Savare on that, and Toscani and Giannazza, right? Giannazza, Savare, Toscani paper. Okay, and if I'm not mistaken, the equation looks like that. So it's a fourth order equation in U, and there is an ugly nonlinear term involving the gradient of U. So in this theory, it's always good to give a different name to U and to the gradient of U. So J is a name for the gradient of U. And then the entropy is just the so-called Fisher information, grad U squared divided by U. And you may know that this equation actually can be obtained, I didn't mention that, but it was important for the thinking. This can be seen as a degeneracy of the Schrödinger equation written according to the Madloom transform when you parabolize the Schrödinger equation. Typically, it's the way I like it, by using a quadratic change of time. Okay, so that's completely a direct fashion to get it from the Schrödinger equation. So it's kind of the parabolic version of the Schrödinger equation. Actually, in the same way as you can see that the linear heat equation is a degeneracy of the Euler equation of isotherm gases. In the same way. So the master equation is Euler and Schrödinger, and then the degenerate equation are the heat equation and the quantum diffusion equation. Okay. Okay, so now, I mean, this is really, this is just to show you how it looks like, but I'm not even sure that the formula is completely correct. So this slide is really a tentative slide. So if I'm not mistaken, because of the homogeneity of degree 1 of the equation, it turns out that we get a little bit like in optimal transport theory, a formulation that looks like the so-called dual Kantorovich formulation, which is actually the primal one, involving the Kantorovich potential. So we get a linear form in phi, subject to a non-linear inequality. So in the optimal transportation case, this would be like the Hamilton-Jacobi inequality. dt phi plus 1/2 of grad phi square is less than 0. But here it's a mess, because we get this thing involving a vector field that you don't know. So it's like a kind of Lagrange multiplier of this expression, which might be wrong. So I know that Giuseppe is writing it down. So I will ask my lawyer to some protection against that. I don't guarantee. I might have made some mistakes in the formula. And anyway, this is very complicated, and I wouldn't expect a nice result that you can solve the optimal, you can find the optimal phi globally from the solution of the quantum diffusion equation. Anyway, there are already some big problems for the quantum diffusion equation. I don't know exactly what is the status of this equation now. I'm not even sure that there is uniqueness. Yeah, so there are a lot of open problems, and so it's quite challenging to look at. And I don't expect let me tell you why I don't expect this method to work globally. Because typically we have to enforce some bounds. Like typically here you see that it's good to have this is the identity matrix. So it's good to have these things to be positive. And therefore we need a kind of a lower bound. And in the scalar case, like the post-medium equation, we get that from the maximum principle in some sense. And then it's very unlikely that this is true in the general situation. So it's maybe then you will get a short time for which this quantity will stay positive, but I doubt this will be true in a global way, which it's a big limitation for the method. But anyway, I think it's fun to look at this problem anyway. Okay, so yes. So now I have a little bit of time. So unless you have some question about the parabolic case, let me just briefly review what I have done for the hyperbolic case. So there will be a slight, short section of hyperbolic equation. So I hope it's okay for most of you. Yeah.
You derive these last conditions as in
yes. Yes, absolutely. Yeah. Yeah. So in principle, this should be a convex inequality, although it doesn't look like. Oh, yeah. Yeah. So actually, this method also is very nice if you want to produce a funny example of convex function for your students, for instance, for your exam, because this creates really monsters, and then at the first glance they don't look convex. So it's horrible. So okay, if I'm not mistaken, if this is okay, this is a kind of convex formulation. Okay. Sorry, if you find mistakes, please tell me. Anyway, I will redo it. Okay, so let me switch back to, I would say last year, when I started this thing. So, okay, I didn't start with 1D burgers. So, but let me show you 1D burgers, because we will see that this is completely linked to optimal transport. So, for 1D burgers, it's almost the same equation as the post-medium equation, but instead of the Laplacian, you have just the first order derivative. It's du dt plus dx of u squared over 2. And therefore, it is quite natural to see dx phi featuring instead of Laplacian of phi. And so the problem is almost the same as the one I wrote before. Okay? And so the only difference is that dx phi is substituting for Laplacian of phi. Okay. And now, and of course, if I use the variable sigma and Q as I did before, then then it is exactly a ballistic optimal transport problem. Okay, it's exactly the same. And actually, it is so similar to optimal transport that I made this statement several times this year. So that if you use, for instance, I use my software, this that I used with, I mean, the thing that we did with Jean-David Benamou in 2000. So he had the software written in MATLAB, and I had the software written in Fortran, because, you know, Fortran 77, so it's a very old thing. Okay, and I tried to see whether I could solve this problem by the software I wrote in 2000, and I had to change 2 lines. Okay, so it's just a matter of boundary condition, and it's 2 lines in a Fortran code. So it's not a code where 1 line means that you solve the Laplace equation in 10 dimensions. So it's really one elementary instruction. So I had to change only 2 lines in the code, because this is like changing the time boundary condition. So it's very simple to do. So it's almost an optimal transport problem. It's very similar. And so in some sense, solving the Burger's equation as an evolution equation amounts to solve this problem. And the nice thing is the problem can be solved globally. That is, I was able to show that if you do that, you can recover the entropy solution of the Burger's equation. In a funny way, because you recover, so given an initial condition U0, you get the entropy solution at the final time, and only at the final time. So it's a strange phenomenon which is related to the fact that the Burger's equation in the framework of entropy solution has no backward uniqueness. So you can get a lot of solution backward in time, and the minimization process, the maximization process, will select only the solution that produce the shock wave at the very final time. So in some sense, you cannot solve, you don't solve the initial value problem in a standard way. So you are given the initial condition, you are given the final time, and you get the right solution only at the final time. And in between, you get something else. So in some sense, if you want to get the full history of the solution, you have to redo the problem many times. So it's not very practical, but at least, because in some sense, the minimization problem will select some shortcuts all the time. So in some sense, we'll change the initial condition, as a matter of fact. Modify the initial condition. So this is like a shooting problem where you modify your angle of shooting in order to produce less problems. So yeah, so I didn't think so much about artillery, but since this is November 12th, so we can still think about World War I, where people were using a lot of guns and a lot of artillery, because most of the people died from artillery. Actually, it seems I read in World War I. Okay, so it was just people were just died because of the shells and the bombs, and then probably the initial value problem is you have U0, and you are not a very good artilleur, I don't know the word in English, and then maybe there are obstacles, or maybe there will be you can shoot on your own troops, something like that. Okay, but the optimal problem will change the angle of shooting, so we'll get exactly the same target, but in a safer way. So in some sense, you preventing any trouble, like troubles means shock waves in this framework, and so this supremum is really able to do that, which is funny. And example 2 is the isothermal Euler equation. So, yes. So let me just show you. So in this slide, I just show you the convex optimization problem we get. So I don't talk so much about the theory. So it looks like that. So it's funny because you have some exponential. So it's kind of a Gaussian. It looks like a Gaussian integral. And so, above you get the isothermal Euler equation, which, as I told you already, is the parent of the heat equation. You can get the heat equation from this if you want, and then so you get a funny problem involving a vector field Q and a matrix a matrix valued field, M, which is a field of symmetric non-negative matrices. And the quantity to minimize is this exponential, this integral of exponential, featuring this kind of Gaussian integral with 1/2q m minus 1q. And there are some additional quantity which are sigma and w, and sigma and w are related to u in capital Q through the linear wave equation. You know, the linear wave equation written as a first order system, the acoustic wave equation. And as I already said in some other circumstances, this is quite funny because it means that the isothermal Euler equation, so I like this phenomenon. So the isothermal Euler equation, you know, it's known that if you linearize the Euler equation, you get the acoustic system. It's a very well-known fact, and this has been proven. But actually in this algebra, without any approximation, I get the wave operator in this funny condition involving u, sigma, w, and q, which means that, so this is typical of the nonlinear thinking. So in some sense, you discover linear equation out of nonlinear equation. And so we know that, I mean, in optimal transport is famous about that because the heat equation has been defined by Otto as a gradient flow in a nonlinear fashion, and there was this fancy theorem, including, I think this was like Ambrosio, Gili Savare, I guess, and giving some, maybe other people also, giving some criterion to tell you that the heat equation is linear. So I love that because it's very funny because this is a part of what I call alien mathematics. So in some other planets, maybe people started the heat equation this way and then discovered I did this joke many times, discovered that, oh, but the heat equation is linear. So maybe there is a Figali who obtained the medal fields in such a planet by proving for the first time that the heat equation is linear, and maybe you can use the Fourier transform. So in some sense you can do, the history of mathematics could be completely reversed. So if you start with Euler, it's nonlinear, and then but also here you can see that you get the acoustic system not by linearization, for free. I mean directly from the incompressible for the compressible Euler. Yeah. Actually, I'm right now teaching a PD course, and I do it all the time like this. So it's crazy. I mean, people will blame me for that. So I start by doing nonlinear equation. I say, well, okay, and then well, you have this poor linear equation, which is just a byproduct of the nonlinear equation. Okay, so the final example is also interesting because it is very similar to the optimal transport problem. So it's a kind of ballistic optimal transport problem, but not for density fields. It's for fields of symmetric matrices. And you may know that this is there is a lot of interest at the moment to try to develop optimal transport in the framework of not of density of probability, but it could be phrased in many ways. So it could be non-commutative probability, free probability quantum mechanics, or also in engineering situations. So people are very much interested at the moment to develop a theory for really fields that are not just density fields, but matrix valued fields. And here, this is a nice example because you see that the beginning at the top is really like the optimal transportation formulation because it's really q squared divided by m, just like in optimal transportation. And there is a continuity equation, which is a linear continuity equation, a generalization of the continuity equation linking the density m and the vector and the momentum q. And you see that it's a linear equation, just like in optimal transport theory. But it's more complicated because of the incompressibility condition. You see that this involves the Riesz transform di dj of minus Laplacian 1, which is a pseudo-differential operator of degree 0. So the whole thing is a linear constant coefficient first order equation. So just like the continuity equation related. So I think this is an interesting example of the situation that you would like to understand better. Although I would say that this continuity equation, so-called continuity equation, is really a big constraint for M. So typically in a standard optimal transport equation, the only constraint for the density is to be positive and to to have constant mass. But here, if M is of this form, you see that this is a really strong differential constraint. So it is really. So I cannot claim that I can treat any matrix field this way, because this matrix field should satisfy this very constraining equation. So it's maybe not a good example, but it's fun to see that just by working on the initial value problem by these convex minimization techniques, we end up with some new problems that are quite similar to the problem that people are interested in for some other reasons. And by this, I think I will stop. Thank you very much.
Very much. We have a little time for questions, comments. Okay, so if not, let's thank Yann again, and we have a short break.
So is it okay?
And
can wait 5 more minutes. Or
Sure, no problem. How do we turn on to... to see this slide?
No, they commute, they do everything. They will
Oh,
take
they
care
will
of
do
it.
it.
Don't worry.
Okay.
It's just.
Yeah, they explain me how
It's
it
already
works.
on, it's already on.
I think so.
Yeah, I think we can start 5 minutes earlier because then maybe there will be more time for questions.
As you wish.
Okay, so maybe you can restart a few minutes earlier, also to leave more time for questions. So it's a pleasure to introduce Zoltan Balogh from Bern University. He will give a talk about geometric inequalities in the sub-Riemannian Heisenberg group. Thank you.
Thank you. So in contrast to Yann Brenier, this is my first time here actually on this conference. I'm very honored to be invited. Thank you, Luigi, for the invitation. I've been many times in Pisa. I always enjoyed it, but not to this conference in optimal mass transportation. Essentially, I would like to talk about this aspect of the optimal mass transportation, which gives you sort of geometric information on your structure and you are working. So of course, the other way of things is sort of obvious, that if you have some geometric information, some knowledge about the geodesics and so on, then you can get insight and results about optimal mass transportation. But this will go in the other direction, sort of the optimal mass transportation will give you then later geometric insights, which is, I find quite fascinating. So this is actually in the spirit of this work of Lot and Villani and Sturm, that sort of using optimal mass transportation, you gain a lot of even definitions of properties related to curvature of domains and spaces, and this is actually the main direction of our work as well. So basically now we would like to get some geometric insight about sub-Riemannian structures, where the geometry is given by a sub-Riemannian metric, and we develop sort of geometric inequalities related to Minkowski inequality and entropy inequalities and Borel-Preskamp-Lieb type inequalities in this sort of setting using the theory of optimal mass transportation. So this is the sort of the goal of this talk. Okay, so this is a joint work with my younger colleague from Romania, Alexandru Cristai, and my PhD student, Kinga Sipos. So first I would like to recall some sort of results from the Euclidean space, which serves us as a toy model how to use the theory of optimal mass transportation to prove actually these geometric inequalities. And then we move on to Riemannian manifolds, and I would like to recall here the work of Cordero Erasken and Robert McCain and Schmuckenschläger. Then we move on a little bit. I will mention just shortly, because of the lack of time, this beautiful theory of Lot, Villani and Sturm about the CDKN spaces, this spaces with generalized lower Ricci curvature bound using the optimal mass transportation. Just touch upon this, and then arrive to a final goal, which is study the sub-Riemannian type of geometries using optimal mass transportation. So this is the plan of the talk. Okay, so the type of inequalities I'm after is the following. So let me recall this inequality due to Borel and then independently proven by Preskamp and Lieb about the same time in the mid-70s. It says the following. It is about three functions. So there is a function h which is estimated from below by at the point 1 minus s times x plus sy. So this is some kind of convex combination of x and y. You should think that this s is fixed, for example, like 1/2 or 1/3 or something. Okay, so anyway, so this function is bounded below by some kind of combination of fx and gy, right? F and g are two other functions. So this MPS of f of x and g of y is some sort of p mean value which is defined here. So if you think that p is equal to 1, then you get the usual kind of convex combination of a and b. But if p varies, then for example, if p is infinity, then this is the maximum of a and b. P is minus infinity, then is the minimum. For p equal to 0, then this is some product of a to the y minus s times b to the power of s. So this is kind of a p mean in that sense. So anyway, so this says that if the function is bounded below by the p mean of f and g, then the integral of h is also bounded below by another mean of the integrals of f and integrals of g, but here the p is changed. Instead of the p, we have p over 1 plus n times p. Okay, so this is the so-called Borel-Prask-Kamp-Lieb inequalities, and that time, of course, the proof was not by optimal mass transportation. It was in Rn, and using the Cartesian structure of the space Rn, it was proved in one dimension, and there was a clever method how to iterate with respect to the dimension to obtain these inequalities for in Rn. And notice that p should be always bigger than minus 1 over n. So it doesn't work for all full range of p's, but starting from minus 1 over n. So actually, if you see for p equal to minus 1 over n, then you get here infinity. Right? So now let's see what is the geometric content of this sort of inequality, because this is about three functions. So if you take p equal to infinity, and then if you take p equal to infinity in this inequality, then you have here on this side 1 over n actually, right? And then if you take f and g to be characteristic functions of some subdomains of Rn, and h characteristic function of the Minkowski sum of the two, and 1 minus s times a plus s times b, then you actually get the Minkowski inequality, right? So the right side will be the integral of this function here, and the left side will be this 1 over n mean of the integrals of these two functions, which is just the measures of a and b. And which implies the isoperimetric inequality, for example. So this is a powerful, very effective inequality with a lot of geometric content, and this is what we would like to pursue also in other geometric settings, not in the Euclidean ones, but first I would like to show you the very elegant and almost straightforward proof using optimal mass transportation, just to serve as a model for other geometric structures as well. Okay, so there are two ingredients of the proof. One ingredient is a algebraic inequality for positive definite symmetric matrices for the determinant to the power 1 over n is concave defined on these matrices, which is this property. So that you take one of the matrix as input, and the output that is determinant to the power 1 over n. This function is concave. And this will be applied for the Hessian of some convex function u, which is both positive and symmetric. And in this way that the convex combination of the identities, so 1 minus s times in plus s times this Hessian of u, determinant of e to the power 1 over n, will be bigger or equal than 1 minus n the determinant of the identity, which is 1, I didn't write it here, plus s times the determinant of the Hessian to 1 over n. So this kind of algebraic fact in a Euclidean space, when we apply, is given by God, so it's just there and we can use it for free. And in other geometric structures, this will be really the issue to prove, such a determinant inequality. Once you prove this kind of behavior of determinant, this kind of some concavity, possibly with other coefficients here, not 1 minus s and s, then we are in a very good position to develop a good theory. So this is kind of the situation. And the other ingredient, of course, is the optimal mass transportation, which I will consider it with respect to the quadratic cost in Rn. And it says, as you know very well, that if you have two probability measures with densities f and g, say, then which are absolutely continuous with respect to the Lebesgue measure, then there exists an optimal transport map, say psi, which is given by the gradient of a convex function. So this is important here. All we need is this sort of characterization, this property of the optimal transport map being the gradient of a convex function such that the push forward of mu through phi is equal to nu, and of course it optimizes the cost, right? So it minimizes the cost. But for us, just this property is important, that it pushes one measure to the other, which is equivalent to the fact, which we call it the Monge-Ampère equation, that G evaluated at psi x times determinant of psi x equal to f of x. And you should imagine for this psi, we put here this gradient of u, right? And for this one, we will combine these two equations, I mean this equation and this inequality, to prove the Borel-Preskamp-Leib inequality. So let's see how we do this. So we need to consider the sort of the interpolant, right, for this S, which is an intermediate value between 0 and 1. We interpolate between the optimal mass transport map, which is psi, and the identity. So for s equal to 0, you are at identity, and s equal to 1, you are at psi. Now we are in between somewhere, right? And psi is the gradient of u. And then we apply the determinant inequality, right, for these matrices. You remember, which we discussed in the previous slide, this concavity of this determinant inequality means that the determinant of the interpolant is bigger than actually the mean, the 1 over n mean of 1, which is the determinant of the identity times the determinant of psi, right? So this is, I write it in this way, this sort of determinant inequality. And then the second ingredient is, of course, the what we have the assumption of the Borel-Preskamp-Leib inequality. You remember that h, this function h, now evaluated. Well, we put here x to be x and y to be psi of x, right? So actually it turns out that we don't even need to use the full assumption about all the x and y's. We just need the y's to be equal to the image under the optimal transport map to be used in order to prove the inequality. So anyways, we have for all x and y, so we pick y to be psi of x. And the assumption in this theorem says that H evaluated at this interpolant is bigger than the p-mean between f of x and g of y, which is now psi of x, right? So we have this kind of two relations, and we multiply them together, okay? If you do this, then we have just the multiplication here, and we see on the left side we have h times the determinant of this intermediate interpolant times on the right side we have the product of the p-mean of fx and g of psi x times the 1 over n mean by the determinant m1, right? So now there is a simple inequality between, so I just copied this slide from the previous one, between these means. This is kind of the Hölder inequality, and it says that if you have the product of such means, this is always greater or equal than the mean of the products if you multiply A and C and B and D here. But of course, then you need to change here the power. So you have a p-mean and a q-mean, and then you have here the right side an eta mean, and eta and p and q are related this way. 1 over eta is equal to 1 over p plus 1 over q, where p plus q should be bigger than 0. And this gives you the actually, we will put q equal to 1 over n, and this will give us this condition you remember from the theorem that p should be bigger than minus 1 over n. Okay? So this is what we do here. And then if you calculate the value of eta, actually, by this relation for 1 over n and 1 over p here, this eta going to be p over p n plus 1, so it's exactly what we need here, right? And we have that the h of evaluated at psi as x times the determinant should be bigger or equal than the p over p n plus 1 mean of fx, and now you need to multiply these numbers here, g at psi of x and determinant of psi of x. But now this cries after the Monge-Ampere relation, right? So according to the Monge-Ampere, this product which shows up here is exactly f of x, right? So then we are taking here on this side the mean between f of x and f of x itself. So it's actually f of x, and then you just can integrate this inequality. So on the right side you have 1, on the left side, by changing a variable here, you have the integral of h, and this is exactly what we wanted to prove. We had some normalization that the integral of f and g is equal to 1. If this is not the case, there is an easy renormalization, and we can deal with that more general situation. Okay, so that was more or less the end of the proof. As you see in 2 pages, using this kind of machinery of optimal mass transportation, we can give a very easy and elegant proof of this powerful inequality. So let's see what can we do in a more general, a more complicated situation of curved geometries. And this has been done by Cordero, Erascan, McCann, and Schmuckenschläger in 2001. Well, actually, I must say that here, that's one paper, but parallel to this paper, McCann wrote another paper. What do you need, essentially, in order to prove this inequality? You need 2 ingredients, right? You need a theory of optimal mass transportation. I mean, how this map looks like. I mean, even in the Euclidean case, we needed to know that the optimal transport map looks like a gradient of a convex function. You need something like that also in the Riemannian setting, and this was done by McCann in a parallel paper. And with his co-authors here, he applied this theory of optimal mass transportation, which he developed in the other paper to prove the Borel-Breskamp leap type of inequality. Well, what did he need to do? He needed some kind of Jacobian or determinant inequality, and this is done in this paper, right? But let me sort of explain the formulation of the theorem, and maybe I indicate some ideas of the proof, such that we see what are the difficulties and how the geometry of the space comes into this theory, into this inequality. So first of all, on manifolds, you don't have convex combinations. So if you have 2 points, you cannot just take convex combination of 2 points. What do? You take some kind of geodesic convex combination, in the sense that you take a point Z, which are on the geodesic between X and Y, and such that its location kind of splits this geodesic in ratios S and 1 minus S, right? And this is this set Z, S, X, and Y. If between X and Y there is a unique geodesic, right, then this point is unique. But if there are several geodesics, then there could be several intermediate points like this, right? So this is generally a set. You can imagine that if you are on a sphere, X and Y are a north and south pole, and say S is 1/2, then this set will be the equator, actually, right? But anyways, in most of the cases, we are concerned with a single point here, actually. Okay, so these are the intermediate points which play the role of the convex combination between X and Y. Dimension big N is the dimension of the manifold. P is bigger or equal than -1 big N. This is just the same condition as in the Euclidean case. Now you have 3 functions again, okay, F, G, and H. And H should be bounded below by some sort of mean of F and G. And that's where the complication comes in, and that's where the geometry comes in an essential way, that there will be some weights, right? So the weights were 1 in the Euclidean case, these V's, and there are some weights which depend on the location of the points X and Y. I will define them in a second. And you will see that these weights actually have a strong relation to the geometry of the manifold. So this is the kind of the inequality in the assumption H and F and G have to satisfy, and then the conclusion is the same as in the Euclidean case, that the integral of H is bigger or equal than the appropriate mean of the integrals of F and G. Okay. So let me go on and explain now these weights. So these weights are defined as follows. Well, maybe I show you a picture. This Vs, X, and Y. You should put a ball around. A ball around Y, right, of radius R. And then take the intermediate points which join this ball to X, right? And take its measure, and then divide it by the measure of the ball, which is shrink by a factor S, right? Maybe I show you a picture here that in Rn this weight is 1. For positively curved manifolds, this is typically bigger than 1, and for negatively curved manifolds, this is smaller than 1. And this is the picture which should maybe have in mind. So let's take first the Euclidean case. So this is, say, X. This is Y here, the center of this bar. And essentially, you do 2 operations with this bar. You take its intermediate point, which is here, so kind of you move it using geodesics towards X, and then you shrink it, this one, and then you compare the 2 measures, and in this case clearly is 1, Thales theorem, and then if the curvature is positive, you will see that actually what you have in the intermediate is bigger, is fatter than when you shrink the ball. So the appropriate V is going to be greater than 1. And if it's negative, then this is going to be less than 1. And let's just think about it. What does this mean for our theorem? So let's move back a little bit to the statement. So you see here, if these are, say, bigger than 1, then this is easier for H to satisfy this inequality, because this is going to be smaller, right? Because you divide by something which is bigger than 1. But if the curvature is getting to be more and more negative, then there is a problem, because essentially these weights here, you can think that if the curvature goes to minus infinity, these weights here will go to 0, and then these expressions here will blow up, and then this theory says that H should satisfy some sort of impossible condition, which nobody can satisfy. So there is no theorem in that case if k is minus infinity in some sense, right? So that's why actually this whole theory works if you have some lower curvature bounds, which prevents you to have k go to minus infinity. Well, kind of the message of my talk is that this is actually not true. You can have a good theory even if you don't have lower curvature bounds in this sense, as you will see later. But let's go on with this. Oops, I go in the wrong direction. Let's go on with the Riemannian theory. Well, maybe I just want to make a comment about this statement. So you see, this is a very hard theorem to check the conditions, because for each point x and y, you need to compute these v's, which is very difficult. Maybe if you have some crazy curved manifold, how can you compute this for so many data? How can you practically check the conditions of the theorem so that you can apply this theorem? Is almost like a nonsense, right? Unless you have some sort of good estimates from below for this v. We saw that actually lower bounds for v are actually important. And the idea would be to get some lower bounds which depend maybe on the distance of the points, between the points, and maybe the curvature or the geometry of M. So that would be the idea. And in Riemannian geometry, there are many results like that. These are called comparison results, which say that you can get some information on your manifold by comparing it with manifolds of constant sectional curvature. Okay? This constant sectional curvature manifolds are spheres or hyperbolic space. They are called space forms. And here are for those, there are very explicit manifolds. For those, these v's can be computed. Okay? And the results say the following, that that if you have so K plays now the role of actually Ricci curvature, and this expression you get for these V's, or actually I would like to call them tau, because this is the kind of usual notation in this theory. So these taus are sort of this sort of V's, which are for constant curvature. The curvature is k over n minus 1. So these are, I mean, so if this is 0, the curvature is 0, then these taus are just s. So the tau tilde, which is essentially v, is just 1, right? So you recover 1 here. But if you have a positively curved space, then you have an expression which you get just computing on spheres with a sign, and if the k is negative, then you have an expression with a hyperbolic sign. But notice that if k goes to minus infinity, this expression here will go to 0. So, and exactly this is the problem. But anyways, based on this lower bounds here, which are given by this data of the lower bound of the curvature and the distance between the points, we obtain some useful expression, or at least lower bound for the weights, which we call them tau, and this theta here actually plays the distance between x and y. And then we get another theorem, or actually a consequence of the previous theorem, which says that actually you can replace those weights over there, these v's, by these taus, which you can compute if you have some knowledge about the curvature and the distance between the points, right? And this is a more useful information. Okay? So I don't know, maybe let's just tell you what were kind of some sort of technicalities which the authors had to overcome to prove such a result in the Riemannian case. Well, as I said earlier, the main, I think the main, one of the main ingredients was the expression of the intermediate map in a form which is similar to the Euclidean, as a gradient of, using a gradient of some function, and this function is as a quadratic cast concave function, but now the quadratic cast is measured in terms of the distance on the manifold. So this is the Riemannian metric on the manifold, d2, d to the power 2. And there is a representation, and this was proven, as I said, by McCann in that other paper, and then you need to prove the Jacobian inequality, so the determinant inequality. And here there were several things which have been used, and one of them is a fact in Riemannian geometry that you can get the expression of some point y if it's not in a cut locus of x as the exponential map. So here the exponential map, it doesn't come for the Gaussian exponential. This is the exponential map on the Riemannian manifolds, and it has two variables, this point x here and this vector here, which it takes in. And here it takes in the gradient of the distance function to the squared from the point y and evaluated at x with respect to the x variable. And using this, you remember you need to get an estimate of the Jacobian or the determinant of the differential of this mapping here. So that is what you need to do in order to get the second ingredient in place. And there is a very cool trick actually, which is where I am now. Right. So there is a very nice trick when you take the differential of this expression here, the difficulty that you need to differentiate with respect to two variables here, this one here and this one. So the exponential map has two variables. One, the space variable where you are, this point, and the other one is the vector which you plug in the exponential map. Let me recall that the exponential map at some point x, right, takes in a vector and it picks a geodesic in the direction of this vector and evaluates it at time equal to 1, right? And so associates to this vector a point again on the manifold. So these two variables is very difficult to calculate, especially nobody knows how to calculate in general differentials of exponential map with respect to this variable x here, and that's a major difficulty. But now the authors of this paper overcome this difficulty by a very nice trick, which I don't have, unfortunately, time to explain, which essentially reduces this complex differential in two variables only about the differential with respect to the second variable, which is the vector here, and according to the chain rule, the differential of this. Well, not really this. You need to make a correction terms here. That's why these whole things work. but the good thing is that this one you can somehow estimate or compute using those weights, essentially. And this part is actually positive, definite, and symmetric. These are some sort of Hessians. And then using this relation, you can play the game and somehow estimate the intermediate determinant. Okay, so now just coming back to those coefficients which we defined earlier, right? And this is, I want to touch a little bit on this point because this really makes the message clear that using optimal mass transport, right, and the behavior of these measures, the entropy functional, the behavior of the entropy functional on this Wasserstein space, and these coefficients here, you can give a notion of lower curvature of very general spaces. This was done by Loth-Villani and Sturm, and the coefficients were exactly the same as the ones you get for manifolds of constant sectional curvature these space forms. And you can develop a lot of theory on this. So actually, you can prove that these inequalities, Borel-Preskamp-Lieb work, as you can prove also some sort of generalized Brun-Minkowski inequality, where you remember in the Brun-Minkowski inequality, the intermediate set is estimated from below by some convex combination of the measures of the intermediate sets here. Again, these coefficients show up, but this can be estimated in different geometric situations. So we get some insight, some gain of information about how the geometry of this structure looks like using this optimum mass transportation. And unfortunately, in a certain geometric structure, which I'm very much interested in, this doesn't work. And these are the Heisenberg group, and Nicolas Juliet was the first one who looked at this case. I was at that time, maybe 10 years ago or so, not much familiar with the optimal mass transport map, but I asked actually Theo, and I asked also Cedric about if this theory of this CDKN spaces works for Heisenberg groups, and they say they don't know, and then Nicolas Juliet said that he knows. Actually, he proved that it doesn't work. So he actually proved that this CDKN condition and also this fails for the setting of the Heisenberg group. So there is no way that we can get it. So these are some sort of singular spaces. We will get into the structure of those spaces in a minute, but they are definitely, they are not included in this framework. And I think the reason is that these coefficients, which they were defined in the CDKN condition, they are like Riemannian, right? I mean, they come from this constant curvature spaces. And actually, it is possible to do some sort of Riemannian approximation of the Heisenberg group, but then you can compute how this Ricci curvature's behavior under the limit, and you can realize that they tend in some directions to minus infinity, and in some directions to infinity, so they go really crazy. So anyways, there is no lower bound, so these coefficients then will be zero, and then this whole theory would not be applicable. Right? Okay, so let me recall the structure of the Heisenberg group. So you should think that in two ways about this Heisenberg group. Either is as Cn cross R or as R to n cross R with a different group operation than the addition. So that makes the group not commutative, right? So it starts well, there is a commutative part, but then in the third coordinates you pick up some sort of skew symmetric product. Good, and then you put some sort of geometry which is left invariant under this, but it's sub-Riemannian. So let me explain this. What does it mean? Let me pick some kind of vector fields which I write as differential operators, and in terms of these vector fields I would like to define the metric. You should think that in the Euclidean case this d over dxi are the metric, are the vector fields, right? But here these vector fields are somehow turning. They are left invariant under this group operation here, but they are non-involutive. So you can have this xj and yj. So these are just the vector fields if you move with the group operation from 0 to everywhere else, and also in the t direction. And we consider a subbundle of the tangent bundle of R2n plus 1, right? Which is given by this first 2n vector fields. So it's a subbundle because they should be 2n plus 1. That's the last one, but we don't consider this one. Consider just the x and the y's here. And then we consider the so-called horizontal subbundle, which is the span of this. And now we define a Riemannian metric, thinking that you put here a scalar product or Riemannian metric, which makes this an orthonormal basis, right? So every time you pick a horizontal vector, you can compute the length of it, of this vector, because now you have a scalar product there. And then you define the distance between 2 points x and y as the lengths, the minimal length of curves which join the 2 points, but the condition is that the curves are horizontal in the sense that their tangent is always in this horizontal bundle, right? So this is a little bit difficult to grasp at once what's going on here, but you can imagine in this way that if you have 2 points, it's like a control theoretical problem that you have a restraint or constraint on the direction in which you can move, but you have to reach one point from one point to the other one. If your vector fields were involutive, right, then by Frobenius theorem, this would be integrable. So kind of you can reach points which are on the leaves of these manifolds, which are foliate the space, and they are tangent to the vector fields. But here the vector fields are non-involutive, so you can reach any point from one to the other. So I don't know if you came maybe by airplane to Pisa. I came by train, but if you came by airplane, you use this kind of geometry because the airplane doesn't go up this way. It makes a turn like this, and this is how actually you can reach one point to the other according to this horizontal curves. We'll see how the geodesics will look like in a second in this geometry. But here they are. Actually, so I think maybe it would be easier for the purpose of the presentation to think that n is equal to 1. It doesn't really matter. So we are in R3 really, right? And you can see that. So considering geodesics from the point 0, from the origin, to some other point. Actually, if I understand how the geodesics look like for this special situation, I can translate it somewhere else. So it's enough to consider just this situation. So I move from the origin to somewhere else. And if I want to move horizontally, then it's easy. I just go along a line. right? And this is the second line, and in this case, I parameterize in this kind of parameter of the geodesic theta is equal to 0. So you should think about this theta about some elevation of the geodesic or curvature or something, right? So if I want to move horizontally, I just use the straight lines. But if I want to move up, right? So you can imagine that here, this is just a circle. So I move along the circle. The projection of this geodesic is the circle. But then I move into the vertical direction according to this here. And this is really a horizontal curve. So actually, the Heisenberg geodesics are lifts of circles. And if you move up, then you just move along the geodesic. There are two the vector which defines the geodesic has two coordinates. There is a chi here and a theta. The norm of the chi, you should think that this will be the distance of the points between the 2 points. And the theta, you can see that actually chi over theta here sort of gives you the center of this circle where you move. So if, for example, theta is equal to 0, then you really have a zero curvature and infinite line as geodesic. But if if theta is positive, then this will be some number. If theta is equal to 2 pi, then you end up exactly above your point where you started from. So this theta also shows you somehow the elevation, vertical elevation between the 2 points. I'm explaining all these things about this theta because it's important. They actually will come in the taus. So instead of the distance, I mean, in the Riemannian case, you remember in those expressions of either the CDKN or the weights and so on, there was a parameter which was the curvature, and there was the distance between the points. Here, the difference that not the distance will matter, but what will matter is actually this tau here, which is, I don't know if there is a common ground to these two theories somehow, because they are so different. Geometric meaning have this kind of parameters which govern the coefficients. But it would be very nice. Okay, but anyways, let's go on. So actually, what is very good in the Heisenberg group that we have this sort of geodesic explicit representation of geodesics, and we have an exponential map because we know the geodesics. The part about the optimal mass transport theory was also developed by Luigi and Severigo. So there is even a kind of a form how the optimal transport map looks like. And a very nice approximation theory about it. If you do Riemannian approximation, Luigi and Severin showed that also in LP norm the optimal transport maps converge. And then Figalli and Nicolas Gellier also have results about that the interpolant being absolutely continuous with respect to the Lebesgue measure. So there are kind of very nice puzzle pieces which just one needs to put together in order to prove the following results. But before defining the results, I need to define the coefficients. Okay? And actually, these coefficients were already more or less calculated by Nicolas Gellier, and the idea is that we have an explicit representation of this exponential map, so we can take its Jacobian and we can really compute this coefficient almost explicitly. So these are the expressions here. Of course, this depends on if you are at theta equal to 0, then you have this expression, and if your theta is somewhere between 0 and 2 pi, then you have this sort of kind of other expressions. So this is a very, I would say, very negative curvature phenomena for this. And for theta between 0 and 2 pi, it's a kind of positive phenomena. Even if theta is 2 pi, this will be infinity, right? So for the theorem, this will be very good, but this doesn't really happen all the time. So actually more, I would say, more this case will happen if you move one set horizontally to the other in an optimal way. So anyways, we have an expression of the coefficients. We have even some kind of elementary inequalities between them. And now if you have 2 points, right, x and y, then you can take the difference between these 2 points. And this point, I mean, this is the group operation, right? X to the power minus 1 is with respect to the group law. And that has a representation in these coordinates chi and theta. And once you have this, then you can associate to these 2 points this sort of coefficient. But I would like to stress again that somehow this theta is kind of the vertical elevation, or this between the 2 points, right? So this is what here comes in, and not the distance as in the other case. And then here is the theorem, but we proved that so essentially the result is that you have a Jacobian inequality where this kind of coefficients come in. Here should be 1 actually, and here the Jacobian of the psi, and so about the interpolant, and then the proof of the Borel-Breskam-Lieb inequality runs as in the usual way. You have, according to the H, some inequality for H and F and some mean, which you multiply again the 2 inequalities, or the other one equality, and you use also the Monge pair, and you integrate and you get the Borel-Breskam-Lieb type theorem. But the question is how to prove this inequality, right? So this is really the question. So there are 2 ways to prove it. One way is to use really the theorem of Cardaliaguet, Skorokhod, and Schmuckenschläger, do the Riemannian approximation, and then because they proved a similar inequality here with some coefficients which they generate, but those coefficients also in the Riemannian approximation can be computed essentially. So although they generate, they don't have a lower curvature bound, but they have limits. And first time we computed those limits in the Riemannian approximation, then we realized that they converge somewhere. So we thought, okay, that's good news. So let's try to prove then the theorem. And but then there are some technical difficulties of how really to estimate this Jacobian, because although according to Luigi's and Severin's result there is an LP convergence, but that doesn't mean that you have a Sobolev space convergence and so on, right? So you don't know if the differential or Jacobian converges or anything like that. But somehow the inequality is going into the right direction, so there is some kind of chain of estimates with a weak inequality, weak version of the inequality, so eventually then we get this estimate. So that would be one way. And the other way was also to directly do the Riemannian proof somehow. And this second way, we discovered later that it works, and actually works in even more general settings than the Heisenberg group. And then you need to develop sort of all these relations which are true in Riemannian manifolds, also in the Heisenberg group and similar settings, this exponential mapping and also this sort of trick by Cardaliaguet, Schmuckenschläger, how to get around, how to get a representation really of the differential of this composite function, but that way it also somehow works even in the sub-Riemannian setting. Right, so then you get theorems as I explained. So this is the weighted BBL inequality for the Heisenberg group, where this kind of coefficients show up. Hours which we computed, so these thetas are these angles here. Then actually you can get estimates which are uniform, right? But of course these are weaker results in the sense that you can even have lower bounds of those coefficients. It's 1 minus s squared and s squared, and even we can have an inequality which is almost like the Euclidean one, but here there is a difference between, you have to pay a price with this exponent here is not p over 1 plus 2n plus 1 times p, but p over 1 plus 2n plus 3 times p, and there is a 1/4 here. So, but we get also entropy inequalities, we get all the relevant inequalities which are actually true for the CDK n spaces in our setting, also Bruminkowski, right? So that was kind of a starting point. Actually, Barilari and Rizzi even extended these results for more general sub-Riemannian geometries, but then the results get at some point so general that you don't really know how to compute these coefficients at some point. So you really need some kind of theory to develop lower bounds of the coefficients for sub-Riemannian manifolds, like comparing with space forms like in the Riemannian case. So this is still a question here. And the main challenge for, and I think it's a very interesting problem, I think Cedric Villani even posed it, to have a common ground of these two theories, such that maybe there is some abstract version where the Riemannian or the CDK and then also the sub-Riemannian is included, but I don't know how to do this, not yet at least. So I think I finished now. Thank you.
Other questions, comments?
Yes, Valentino.
Thank you. Just concerning the last question about the possible common ground, do you have any idea of how you could explain the fact that you take the square root with respect to the topological dimension of the group instead of the metric dimension? So the fact that we have 1 over 2n plus 1, that is q, so the metric dimension minus 1. So is there any idea to make the metric, the Hausdorff dimension to appear?
No, I think the main question here, what I was alluded to, is that in the coefficients, right, in the expression of the coefficients geometrically in the Riemannian case or CDKN case, you have these 2 points, right, and the distance between the 2 points is relevant. That is the data which comes into the coefficient, and you can imagine that if you go from one point to another and you have some lower curvature bond, this could accumulate from point to point, and if the points are far away, a lot of curvature can accumulate, so that coefficient can be very bad because of that reason. In the Heisenberg case or sub-Riemannian case, it's not the distance between the 2 points which gets into the coefficient as a data, but that theta, that angle. So the points could be very far from each other, right? But if the theta is not so, I mean, it depends on this theta, not the distance. This is essentially the problem, to get a more abstract theory where both these aspects are considered, or as particular cases. But I have no idea. About those coefficients, these are just coming out of the formulas, what you asked about the exponents.
Okay.
I don't have a geometric explanation of that, but they are, you know.
Maybe this could be the
Yeah, we
first
can
obstacle in order to find a background theory.
Maybe.
Thank you.
Any more question, comment? Aspetta un attimo.
So I was wondering if these inequalities are sharp in some sense. Do you have an idea? Because the Brun-Minkowski, for example, you can check on both. You have equality, right?
They are sharp. They are sharp. First of all, Nicolas Juliet showed that this is sharp by examples. This is how he got his result that the CDKN condition fails, by exactly looking at what happens in the intermediate. And we also have some related examples showing for other cases that these are sharp.
Okay. Any more questions, comment?
Yeah,
Nicolas.
Thank you. About just Riemannian geometry, if you have no bound on K, can you no lower bound on K? Can you do something with the Borel-Braskamp inequality?
No, probably not. No, I believe not. But what is the advantage here in the Heisenberg case, that if you have for example, looking at Riemannian approximation, which you know very well, if you calculate these Ricci curvatures in some directions are minus infinity, but in the other direction is plus infinity. So there is some compensation effect, I think, between these two, and that's why they will converge to a limit. But if you have just minus infinity, I think there is no chance to do anything.
Okay. Any more question, comment? Okay, so if not, let's thank Professor Balogh again, and we have now coffee break. From the University of Paris-Dauphine, he will talk about on the master equation in me-field games. Thank you.
Okay, thank you, Luigi, for the introduction and the invitation. It's really a great pleasure to be here again. I was not in the first conference in me-field games on optimal transport. I think I was in the second one. But so I will discuss about mean-field games. So Yann explained that it is related with optimal transport. In fact, the usual mean-field game system is really a small generalization of the usual forward-backward optimal transport system, where you have this coupling between a Hamilton-Jacobi equation and a continuity equation. So here I'm going to discuss about an equation which is above this system of this coupling system of Hamilton-Jacobi equation and continuity equation, which is called the master equation, and which was introduced by Lyons about 10 years ago. And I will present some kind of new construction for this master equation, which are a little bit complicated. So far the construction, the existing construction take a lot of time, and the idea was to simplify a little bit how one builds solutions. So this is the ongoing work with Marco Cirant, who is postdoc in Padova, and Alessio Porretta, who is in Rome. Okay, so the master equation is an ugly equation, so I'm going to give you two of them. The first one, which is the second order master equation, and the second one, which is a master equation with a major agent. So besides being both ugly, they have a common point. So there are several common points. So in the first one, the unknown is a scalar function, capital U, which depends on time, space, and probability measure on the space, and we satisfy an equation on this space. So the first part, you recognize the standard backward Hamilton-Jacobi equation where you have only local derivative, and the rest of the term, which is really awful, relates the derivative of the unknown u respect to the measure with the rest of the data. Okay, so the data are typically mostly the Hamiltonian here. Okay, that you find again here. HP is the derivative with respect to the gradient. So derivative. So you have the Hamiltonian, which is given, okay, with the derivative here, and the beta, which will be called the common noise. We'll see that later. And finally, the terminal condition. So this is an equation stated in the space of measure with the terminal condition. So it's the same kind of equation for the master equation with a major agent, where you have now two unknowns, U0 and capital U, and they both satisfy quite non-linear equations. Okay. So how do we understand this equation? So they arise in differential games, so meaning optimal control problems, where you have a very large number of players. So in principle, they should arise as the number of players go to infinity. And their main feature is the fact that they are non-local, they are non-linear, and they don't have a maximum principle. Okay, so that's important. And in fact, that's one of the main difficulties, is the fact that you don't have the ordinary tools to handle this kind of non-linear Hamilton-Jacobi equations. And in addition, they are stated in the space of measures, which makes them not easier. There have been several works on that equation. So they were introduced by Lasserie and Lyons around 2013, and investigated a lot since then by various authors. So let me mostly quote maybe the first one who handled really this kind of equation in a relatively simple system, simple framework where you don't have diffusion at all, was Gambo and Zwiek. And the first equation where you don't have beta, so this beta was handled by this paper by Chassagneux, Crisan, and Delarue. And with Delarue and Lasserie and Lyons, we studied the second order one. Okay, so this one, and we prove the existence and uniqueness. So what I want to do here is to explain how to simplify the construction of this equation, which were really, really a mess. Okay. So I'll do that. So I'll present this construction in 3 steps. In the first one, I will explain how to build solution in the simplest framework of a first-order master equation. Okay, where you have no common noise, you don't have a major player. Okay, and where the intuitive interpretation of the equation is relatively easy. And then I will explain how, building on this first-order equation, we can build solution for the common noise problem and for the major problem. So in this first part, I will recall results we obtained some time ago on the first-order master equation and the interpretation of this master equation, and show a little bit also how they are related with the optimal transport problem. Okay, so the first-order master equation arises as the limit as the number of players go to infinity of an optimal control problem in which you have capital N players. So you have capital N players, and for each player has a dynamics, which is a stochastic dynamics, where he controls his drift. Okay, and you have a Brownian motion here. And I'm assuming that all these Brownian motion are independent. Okay, so you have a very large system, and each guy choose his control in order to minimize the cost, which has a very specific form. Okay, so the assumption I'm doing is mostly on the cost of the players, which consists in integral cost and terminal cost. So the integral cost consists for player I. It consists in the position of player I, the control he plays at the time, and the empirical distribution of the other player. So players do interact only through their empirical distribution. So for player I, he doesn't care about the control played by the other player, but only on their position. Okay, so typically you can think about what happens when you are in your car and you try to go from one point to another point, and you have plenty of other people doing the same kind of solving the same kind of problem. So you interact with the position of the other people, which prevents you to go as far as you want, as fast as you want, and so on. Okay, so this is typically the kind of problem we meet. And there is a terminal cost, which, and there is a small typo, it should depend also on the empirical measure. Okay, so this is, this Lagrangian here is typically a quadratic function of the control one plays, and cost for the interaction between player I and the empirical measure. Okay, so the goal of player I, the goal of each player, is to minimize a cost of this form. And as you are probably aware of, in game theory, you don't have a notion of minima, but you have a notion of equilibrium, which says that basically, given, so an equilibrium is a collection of controls, let's say, to simplify, such that if one of the players deviates, then his payoff gets worse. So I'm considering alpha bar 1, alpha bar n. This is the cost for player I when all the players play alpha bar 1, alpha bar n. And if one of the players, if player I deviates, he gets a worse cost. Okay, so if he plays alpha bar I instead of alpha bar I, he gets something else. Okay, and what we'll be interested in the value function given in that way. So here, these guys are the initial position of the game and time t0. Okay, and I'm interested in that. And what we want to understand in these problems is the limit as the number of players go to infinity of this function. Okay? So here comes the PDE. So it turns out that this function satisfies a system of PDE, which is the following one, which is we call the Nash system. So it satisfies the Hamilton-Jacobi equation again, okay, where you see here the usual Hamiltonian, okay, which is given just by the convex conjugate of the Lagrangian appearing in the cost of the players, okay, and there is and the interaction between the players is, you can see it. This is the value function for player I, but it's perturbed by the position of the other players through the Laplacian and through these terms, okay, and now you can argue by. You can look at the equation and see, which is again a backward equation, which is parabolic, and if you make enough condition on H, you can prove that there is a unique solution of this equation. And because of the symmetry of the equation, what you expect is that as the number of players goes to infinity, basically the value function of this player, which is a little bit complicated, simplifies into an equation where into a variable where which depends only on time, on the position of player I, okay, and on the distribution, the limit distribution of all the other players, okay. And this guy, if you pass formally to the limit in this system, it should satisfy what I call the first order master equation, which is this one, okay. So there are terms which are more or less transparent. The time derivative of Vi should converge to the time derivative of U. The Hamiltonian part should converge to the Hamiltonian, so here there is no mystery. Somehow, in this sum, you've got the Laplacian with respect to xi, which is big, okay, which converges to the Laplacian with respect to x of the function capital U, and the other parts, okay, which are smaller because player interact only through their empirical measure. So for player I, the size of player j is more or less 1 over n. Okay, so in this sum, you've got the Laplacian for player I and the other Laplacian, which are of size over order n, and more or less by the law of large number, what you should expect is that this should go to some average, and this average is here. Okay, this is this quantity. Exactly in the same way, in this sum, you take the derivative of respect to xj of the value function of player I, okay, for j not equal to I. So this is of size 1 over n, that you integrate against this vector field, you sum against this vector field, and this guy should converge to a quantity like that, okay, and in both cases, what you have here is the derivative respect to the measure. Okay, so this is what formally one expects, okay? let me say a few words about this derivative with respect to the measure. So we work as usual in P2 over D, endowed with the Wasserstein distance, and we will say, so I'm always working with very, very smooth function, okay? So in contrast with what is usually done in optimal transport theory, here all my function will be more or less infinity on the space P2, okay? So what I say that the map U is of class C1 if it's the integral of its derivative. So its derivative is a function depending on measure and an extra variable, okay? And I'm saying that it's C1 if you can write U of M prime minus U of M as the integral between 0 and 1 of the integral over the space of delta U of the delta M, okay? Against d M prime minus M. So basically the difference is the integral of the derivative, basically, okay? And what we said, and it would be convenient to call the Lyon's derivative, this derivative, the derivative with respect to y of that guy. And it turns out that if you're familiar with the derivative in the space of measure, this is the derivative in the usual one, okay? So let me be this more specific. So this function, you see that it's integrated against two probability densities, so this is of mass 0, so this expression doesn't see the constant, and there is a very natural way to normalize that, which is to assume that my derivative has integral 0 against itself, against the measure itself, okay? So that's a convention that we won't see much, and this function dmu corresponds exactly to the derivative in the space of measures that you can find, for instance, in the Ambrosio Gilles Savare's book. And this derivative is important since it controls the Lipschitz norm of U, if you like. Okay, so for instance, you have this kind of inequality. Okay, so the derivative which will appear throughout the Stokes is more this one, but for computational reasons, this is the one we use all the time. Okay, so what do we know about the master equation? So we know that there exists a solution for small time interval, okay? So without extra condition, you have always a small existence on a short interval, and you have even, if you make some structure condition, which is called monotonicity, you will have existence on a larger time interval. So to do that, we have to assume that the Hamiltonian have a separate form, okay, which can be written as H naught, which depends only on the position and on the gradient here, P, minus a coupling term, which is called here capital F, depending on position and measure, okay? And we assume that F and G are monotone, so G is the terminal condition. F and G are monotone, meaning that if you take two measures, if you compute F of M1 minus F of M2 and you integrate against M1 minus M2, this is non-negative. So heuristically, in most examples that we can consider, these conditions mean that people don't want to be close to the other people. So it's people want to be as far as possible as the other ones. Okay, so it's a stabilizing condition which explains why you can have existence and uniqueness for large time. So how do we prove this kind of existence and uniqueness result? By the method of characteristics. So, Harry, sorry, I forgot to say something. Yeah, so I told you about this existence uniqueness for the master equation. One of the main interests of building master equation is to prove this kind of result. Remember, I told you first that we were interested in the Nash equilibrium configuration for n-player game. And you have to, and here is a proof, here is a statement that the n-player game converges to the master equation, okay? So the value function of the n-player game as n goes to infinity is controlled by something like C over n, okay? Something like that. Okay, so as I told you, in general, you don't have existence on large time of the solution of this master equation. And one of the reasons is the following. It turns out that what we expect when the time goes large is that the solution U develops discontinuities. I will try to give you an explanation of that in a moment in a particular case. And so far, and this is probably the main open question in the field, and one of the reasons why I wanted to present this kind of result here, is that we have absolutely no clue how to define a weak solution of this equation. Okay, so we will see in a moment that this kind of transport equation on the space of measure, but no weak solution. Okay, and in particular, when we don't have a classical solution of the master equation, we don't know if this kind of result holds. Okay, we have no clue about the convergence of that guy. So now I want to explain how to prove the existence of a solution to that guy. And we'll see that it relies on the method of characteristics. So if you know a little bit about mean-field game, you have seen this system, which is the mean-field game system. So let's fix an initial position in initial time t0, initial measure m0, and let's look at a solution, a finite dimension solution um of depending only on time space. Okay, so here no dependence in respect to measure of this system. So this is a finite dimensional system of equation where here you've got the Hamilton-Jacobi equation backward, and here you've got the forward Fokker-Planck equation, which is more or less the classical Fokker-Planck equation with a terminal condition, which is the usual one. Okay, and the initial condition for the measure, which is m of t0 equal m0. Okay. So now we are back on the finite dimensional space, and this system is very close to the optimal transport system I alluded at the beginning if you don't have the Laplacian. Okay, so if you don't have the Laplacian and you have h, which is just a half of gradient q square, okay, you recognize here the familiar system of the familiar coupling between Hamilton-Jacobi equation and continuity equation. Okay. So this is just a small extension of that. So for this system, we know that if t is small or under monotonicity condition, you have a unique solution. In fact, for this system, if t is large, you also have existence of solution, but you lose uniqueness. And okay, and how do we build a solution of the master equation using this system? It's very simple. You just solve this system and decide that u of t0 x m0 is equal to u of t0 x. Okay, so to do that, you have to start with the initial condition m, solve the Fokker-Planck equation, solve the Hamilton-Jacobi equation backward, come back to time t0 to have that. Okay. What I claim is that this gives you a solution of my first-order master equation. Okay, so let me show you the proof of that fact, so of that claim, assuming that u, capital U, is very smooth. Okay, so here it is. So the first thing is that one thing you can note is that, of course, so here I start from time t0, but if I start from time a later time t1 with the measure m of t1, I've get of course the same solution of the master equation, okay, the mean-field game system. Okay, so I say it again. If I start at later time with m of t1, okay, because of uniqueness, I've got the solution, the same solution. So what I'm claiming is that if I take h positive and I look at u of t0 plus h, this is equal to u of t0 plus capital U of t0 plus h, m of t0 plus h. Okay, so and now I'm going to use this obvious relation to derive the master equation. So I'm going to take the derivative with respect to h at h equals 0 on both sides, and look what's going on. Okay, so let me start with this one. Okay, so the derivative of that guy, which is the derivative of that guy also, is the derivative in time plus the derivative with respect to the measure times the derivative of the measure. Okay, now I'm using the equation for m, which is here at time t0, okay, which gives me the Laplacian plus the drift term, okay, and I'm integrating by part to get the Laplacian here and the divergence here, okay, and I'm using the definition of So for instance, the definition of the Lyon's derivative, let's say, to get dm on the one hand, and when I do two times derivative, I got this term. Okay, so this is here the non-local terms involving the derivative with respect to the measure. On the other hand, I'm using now the equation for u. Okay, u satisfies the Hamilton-Jacobi equation, so you've got that, and it gives you, I mean, since this relation involves only space derivative of u, you get the same relation with capital U instead of small u. Okay, and when you say that both things are equal, okay, I mean that this is equal to that. Okay, this gives you the solution of the master equation, first order master equation. So this is more or less a triviality. Okay, so it's really easy. The only thing you have to check is that this equality defines a smooth function with respect to the measure, and here you have to work a little bit. But in that framework, was a mean-field game system, the characteristics is relatively simple. It's not difficult. Okay. Okay. So I just want to make a small detour to show you why one expects to have shocks when you have multiple characteristics. So for that, I'm going to work in a case which is called the potential case, where I assume that the Hamiltonian is separate. So he has this form. And remember, when we were in the monotone case, I was assuming this kind of relation. And I'm assuming that f and g derive from a potential, okay, meaning that they are derivative of some, okay, of some function which should not be the same. Here it should be another f and another g. Okay, so they derive, the true coupling f and g derive from some function f tilde and g tilde. Okay. So this is my assumption, and what I'm going to show you is that in this case, one can more or less relate the solution of the master equation to an optimal control problem here in terms of kind of Benamou-Brenier formulation. So let's look at this kind of Benamou-Brenier formulation. So we are minimizing, again we fix an initial condition, T0, M0, okay, and we are minimizing again the control alpha, an expression of that kind, okay, which is typically a half of alpha square times m, okay, plus the coupling term, the integral of f of mt, plus the terminal cost, okay. So compared to Benamou-Brenier, you don't have you don't have that in Benamou-Brenier, and you have here alpha square, okay. And you take the constraint, the usual constraint, continuity equation for coupling here because you have Laplacian. Okay, you have this relation. So this is, you minimize this guy, this constraint, and in fact, if you do that, what you end up is a solution of the mean-field game system, more or less, which appears as a necessary condition. But let's forget about that, and let's look at this guy, this function capital U, as a function of T0, M0. Okay, so this is a value function of in the space of measure of an optimal control problem, which is in the space of measure. Okay. So, what one can prove is the fact that so this new function is a classical solution of a Hamilton-Jacobi equation, which is expected because this is an optimal control problem. Okay, so it's related to a Hamilton-Jacobi equation. The relation with the first order master equation is the following. If you take the derivative with respect to the measure of this function, okay, then you end up with the derivative of the in space of the function u, okay, which is the solution of the first order master equation. Okay, so this relation explains you what is how to relate this kind of computation with the master equation. Okay, so somehow you can find the solution of the master equation in this particular case through a global minimization problem and not a fixed point problem. Okay. Now, when you have multiple characteristics of the master equation, this means that in this case you have several solutions, several minimizers here. Okay. You can the derivative respect to u becomes discontinuous, and therefore the function in capital U becomes discontinuous. This is the reason why one expects discontinuities of the function u when you have several characteristics. Okay. Okay, so let's move now to the construction of to the more complicated equation. So this one is really well understood. The first order master equation is really well understood, and it's not too difficult to manipulate. Now we go to the more complicated one, where we add common noise on the one hand, or major player for the last part. Okay. So I'm going to do 2 times more the same thing, looking at the heuristic explanation of the equations, and then saying how one builds a solution. So for the second order master equation, we have at the level of the n-player game exactly the same dynamics, exactly the same cost for the player, exactly the same notion of Nash equilibrium. The only difference is that in the dynamics of the player, you've got an extra term. So as I told you, in the dynamics of the player of the n-player game, you have the control part, the Brownian motion for each player, okay? And now we have an extra Brownian motion which somehow perturbs the dynamics of all the players exactly in the same way. Okay, this is the W here. I'm assuming that all the Brownian motions are independent, but here this Brownian motion does not depend on the index I. Okay, so all the players are perturbed by in the same way. So think about my example of driving a car. What I'm assuming here is that there is some force which is shaking all the players at the same time in the same way. Okay, so there is a randomness. Some strike somewhere in Paris, which happens sometime, okay, which perturbs completely the system and affects all the players in the same way. So this is this guy, okay. Now, what does it change in terms of equation? And again, I want to look at the value function of all the players, pass to the limit. So what does it change? It changes the Nash system in the following way. So for the Nash system, it only adds this extra terms, which is the impact of the Brownian motion, the common noise. So beta is, I'm sorry, I forgot to say that beta is the level of the common noise. Okay, when I take beta equals 0, beta is scalar. When I take beta equals 0, this vanishes. So here it just affects the Nash equilibrium through this term, which is quite natural. Okay. And now, when one wants to pass to the limit in this system, exactly as I did before, what one finds is several extra terms involving second order derivative with respect to the measure. Okay, so they are really awful. So there is a way to prove existence and uniqueness for this equation, again through the method of characteristic. And this is what we did with François Delarue, Jean-Michel Lasserie, and Pierre Williams. We use this method of characteristic, but now the method of characteristic is really bad. It's bad in the following reason, for the following reason. So this is what I just said. Okay, that you can use, can prove existence and uniqueness of the solution, and even we can prove the mean-field limit. But the method of characteristic is bad because the characteristics are now random, in the sense that M satisfies a random Fokker-Planck equation with you have the random drift here, and U satisfies backward Hamilton-Jacobi equation, which is now random. And because it's random and backward, it has to be adapted to the filtration generated by the Brownian motion. So you have to have an extra, exactly as in backward equation, you have to have an extra term which ensures this adaptivity. Okay, so you've got something which is really horrible, and it takes 50 pages to prove only the existence of a solution to that guy. So it's really, really awful. Okay, let's say. Okay, so that was the method we devised with François Delarue, Jean-Michel Lasserie, and Pierre Williams to prove the well-posedness of the solution. Okay. So what we found with Alessio Porretta and Marco Cirant was a way to bypass these stochastic characteristics, and we are doing it in the following way. So what we see is that this second-order master equation, where you have these beta terms which take into account the common noise, we see them as a superposition of two equations. So the first one is the one where you don't have the where you have beta equals 0, so you don't have the common noise. So this is the first order master equation. So we see it as the superposition of the first order master equation, and the other term where you have only the beta, okay, which is called the second order master equation, linear. So this is the reason why we call it L2. Okay, this is the linear second order master equation, which is completely linear in U. Okay, you don't have a, okay. So you have this superposition of these two equations, and the idea to build solution is very easy. We are going to alternate the two schemes. The first one involving where we solve the first order master equation in very short time interval. Then we alternate the second order master equation, and we go on like that. Okay, so we do a kind of Trotter-Kato scheme in this framework. Okay, so now for the second order master equation, it's extremely easy to do because we have explicit formula. Okay, let me show you. If you look at the heat kernel, okay, this is the terminal condition of my problem. I look at this equation, I look at this expression, and this gives me a solution to my second order master equation. So here it's completely straightforward, okay? And it's two-page computation to show that this guy gives you a classical solution to that guy, and you have to do a little bit computation in the space of measure, but it's relatively easy. So now let me show you the short time existence for my second order master equation. You look at the backward semi-group associated with the first order master equation, then you look at the backward semi-group associated with the linear second order master equation, and you alternate, okay, by a Trotter-Kato scheme. And what you can prove is that under some smallness condition on the time interval, okay, you have a solution to the master equation, to the second order master equation, okay, by this way. Okay, so it's explained like that, it's almost trivial. Now you have to work a little bit because you cannot alternate like that. I mean, Trotter-Kato doesn't work, that does not always work. So you have to get to do that, proving estimates. And the estimates you have to prove are like that. So U is the solution of the first order master equation, and you have to manipulate it in order to ensure that the regularity of U in space and measure does not deteriorate too much the regularity of the terminal condition in space of measure. So too much meaning in a linear way in time. Okay, so that's the heart of the proof. Okay, so which ensures that in fact when you alternate the two subgroups, okay, you don't deteriorate too much the regularity of the guys. It turns out that you can do the same thing for the master equation with a major player. So now let me explain you what is this master equation, what is the major player problem. So it's the same kind of problem as before, except that you have one guy which weighs a lot, much more than the other ones. Okay, so it's a mean field game problem in which each small player looks at a big one and takes his action in function of this big one. So more precisely, the dynamics, so now I've got n plus 1 player, I equals 0 is the major player, I above 1 is the minor players. They have the same kind of dynamics, so nothing new here. But the cost differs from the player I equals 0 and the player I above 1. For player I equals 0, he looks only as before, as his position, his control, and the empirical measure of all the players. For the small players, they look not only at their position, but also at the position of the big one, okay, of the big player, and like that. Okay, so typically you have a guy who influences the crowd through his position and his dynamics. Okay, so this is the only novelty in my story. Okay, this term here. Okay, and again, you expect you define Nash equilibria, and you want to find the mean field limit. So here, obviously, you lose the symmetry between all the players. So there is the big one and the small one, and so you will have two different value functions, so two different limits, one for the big one and one for the small one. So the limit for the big one depends only on his position, the initial time, his position, and the density of the players, while for the small one, the limit should depend also on the position of the big player. Okay, the x naught, which is the position of the body player. So, okay, so I wrote the Nash system, but there is nothing new under the sun, except that I had to write different equations if I look at the big player or the small one, because they are not completely symmetric here. And the midfield limit should be a system of master equations. Okay, so it's completely obvious. It's completely awful. You wouldn't like to handle this kind of stuff, and in particular, the method of characteristics seems completely impossible to put. I mean, we have no clue how to make it work. Okay, by method of characteristics. Yeah. So. Nothing. There is a Lagrangian here, okay, which is different from this one, and this one depends also on the position of the major player. Okay, so they interact through the empirical measure of all the guys, but here you see that there is the position of the big player, which is here and that's all. Okay, so that's all. It's surprising that it makes such a big difference at the end. Okay, so, but that's the only difference at that level. Okay, and this is responsible for a huge difference between the master equations. So as I tried to say, I don't know how to handle that by method of characteristics, so in principle it's a little bit desperate. But it turns out that if you use this Trotter-Kato scheme that I presented before, it's almost straightforward. So it's a small miracle which says that if, in fact, the system decouples completely, so it decouples in two parts. Okay, so this is our main result, which says that we know how to prove the well-posedness of this solution in short time. I forgot. Well, that's completely wrong. It's not monotonicity condition. It's only in short time, and we prove the mean field limit also. Okay, and the way we do that is the following. So we see this monster equation as a superposition of two equations. The first one is the first order master equation. So you recognize here, for u, it's just the term you saw in the first order master equation. And for u naught, it's just linear with respect to u naught once u is given. Okay, so this part is very easy. Okay, so here, x naught is frozen. Okay, so the position of the big guy is frozen. And I'm just solving a system where this is the difficult part, but this is just the standard first order master equation. Okay, and this is something which is linear with respect to u naught, so it's relatively easy to handle once you have solved this one. And the other part, well, if you look at the remaining terms are just here it's Hamilton-Jacobi, okay, and here it's also Hamilton-Jacobi, where u naught can be solved independently of if you solve first u naught and you've got something. So you see this decoupling situation which pops up and which gives you exactly the theorem I alluded here, well-posedness on short time, and once you have the well-posedness, you can prove the mean field limit. Okay, so I'm almost done. So what I try to explain here is how to build solution to this awful equation consisting in the master equation, which plays really a central role in theory. Okay, and there are several things which are relatively easy extension. But what I want to emphasize is the fact that there are two big questions. One which is really completely open, and we really want to have answers to this question, which is what kind of notion of discontinuous solution can we devise for the master equation? In particular, do we have the mean field limit when you lose the existence of classical solution of the master equations? This we don't know, and that's one of the big things. Another thing which is more astonishing is the fact that I presented the result for the minor problem for short time interval, and as I told you, for second order master equation, if you put some monotonicity condition, you have existence on the large time interval. We have no clue about structure conjunction for the minor problem to prove long time existence. And I thank you.
Questions, comments? Okay, so thank you again, Pierre. Anticipate a little bit, we just make a 5 minutes break and then we start a few minutes before, okay? So the last talk of this morning is by Shouhei from Tohoku University. He will be speaking about embedding of RCD KN spaces in L2 via eigenfunctions. Thank you.
Thank you very much for introduction. And first of all, I'd like to express my appreciation to the organizers for giving me this opportunity. This is the second visit in Pisa. The first one is 2 years ago. So for 1 year, so it was so nice. So now I'm really happy for coming back to here. Okay, the title of this one. Okay, please wait. Maybe. Okay, perfect. Oh, this is a joint work with Luigi Ambrosio and Jim Portuguese and David Theodoros. Okay, so since I will use several constants, so many constants, so I'd like to introduce what is the meaning of the constant. Okay, there are so many colors. Okay, please wait. Okay, for this red color means a dimension, or its upper bound. It's upper bound. Okay, and blue means a lower bound of curvature. Okay, and this is okay. Green is upper bound of the diameter. But it's difficult to distinguish this one. Okay, the purple is a time. Okay, purple is a time. And brown is a kind of the non-collapsed constant. Okay, and the pink is a small positive number. Okay, let's start. Okay, it's okay. It's okay. Okay, the section 1 is the introduction. Introduction. Okay, let's start by a very famous theorem by John Nash. Okay, this is a Nash theorem. Okay, let us fix a closed manifold. A closed manifold. Closed means compact without boundary. Okay, the N is a dimension. Then the conclusion is this manifold can be embedded to high dimensional Euclidean space by isometry. Okay. The isometry means, of course, the pullback Riemannian metric coincides with the original one. It's okay. So the ST means the standard. It's okay. So ST means the standard. It's okay. Well, this is the Nash theorem. Okay, here is a remark. But this map is not canonical. Okay, canonical means we cannot write down explicitly. It's okay. Then the Nash theorem states the existence of this one. On the other hand, I'd like to introduce another related result, which was proved by Green. The statement is as follows. We fix an open manifold. The open manifold means complete and non-compact Riemannian manifold without boundary. Okay. Then the conclusion is the open manifold can be embedded to a 2n plus 1 dimensional Euclidean space by harmonic map. Harmonic map. Okay. So in particular, all open manifolds has a non-trivial harmonic function. Is okay. Here is a remark. This cannot be extended to the closed manifold. Of course, because any harmonic map from closed manifold to Euclidean space is trivial. That is, the image is 1 point. It's okay. So we cannot extend this to closed manifold. Instead of this, Here's the theorem. Not isometric, yes, but the map is proper. It is so nice. Then here is this theorem is proven by Balogh, Besson, Gall. Okay, they use eigenmap, which is also very nice natural map from closed manifold. I introduce the theorem. Here the theorem is this. Phi t is a map from Mn to L2 space. It's okay, L2 space. What is phi t? The t is a time parameter. Is this one. Okay. By using a heat kernel. Okay, heat kernel. So the Mn is, of course, this is a closed manifold. And P is a heat kernel. Okay, heat kernel. Then the conclusion is as follows. Then the map is smooth embedding for any t. Okay, for any t. And moreover, they proved the asymptotic behavior of the pullback metric. As t goes to 0, then the following asymptotic formula of pullback metric holds. Okay, let us consider the pullback metric, phi t star. But in order to simplify our argument, it is better to multiply a normalized constant. What is the normalized constant? The normalized constant we adapt is this one. Omega n times t and the power of this one. Okay, then the asymptotic behavior is this one, where the omega n and cn is a positive constant. It's just positive constant, defined by this one. Maybe I think omega n is a standard notation, which is the volume of the unit ball in Euclidean space. Yeah, it's so nice. But Cn is a little bit strange, which comes from the heat kernel of Euclidean space. It's okay. But this is a partial derivative. It's okay. This is a partial derivative. Okay, this is a expansion of pullback Riemannian metric. Then the key point is the first principal term. In the first principal term, then the original Riemannian metric appears. Then the second principal term includes the curvature term. Is a curvature term. So to simplify this convergence result, so let's divide constant Cn in both sides. That is this one. Scalar means a scalar curvature. The rich is a rich tensor. Okay. Then, to be more simplified, so let us put this map, this part, is denoted by phi tilde t. Okay. This is more simplified notation. It's okay. Then this theorem states this one. It's okay. But this is the starting point of my talk. Okay, but this embedding, then the target space is infinite dimensional. Okay, so I'd like to consider the finite dimensional reduction of this map. Okay, so how to get such finite dimensional reduction? Our setting is this: Mn can be embedded to L2 via phi t. Okay. Since Mn is a compact, so there is a canonical basis. There is a canonical basis of L2. That is this one. Okay. But what is phi I? The phi I is a eigenvalue of Laplacian. So the phi I is also orthogonal basis of L2. Then it's easy to find a nice n-dimensional subspace of this one. That is this one. Okay. It's okay. This is a canonical n-dimensional subspace of L2. Of course, this is isometric to Euclidean space. Then we can define the finite dimensional reduction as follows. It's okay. This is very natural one. Then of course, the normalized version is also defined by the same way. That it is. It's okay. This one. Well, this is a definition of phi tilde mt. Okay, here is a theorem, which is proven by Portuguese. Then the statement is as follows. So we first fix epsilon. It's okay. So fix epsilon. Then there exists a time t0, which is depending only on dimension and lower bound of curvature and upper bound of diameter and some non-collapse constant tau and epsilon. Okay. Such that for all t is at most t0. Then there exists a number n0. N0 is depending only on nk d tau epsilon t. Okay. Such that the important point is that these constants are given by a priori. Okay. If manifold satisfies the following three conditions. Okay, this is a rich curvature is bounded below by k, and diameter is bounded below by d, and injectivity radius is bounded below by tau. Inject ING. This notation is means injectivity radius. Okay, then the conclusion is this one. Then the finite dimensional reduction map is smooth embedding, and the differential of this map satisfies this one for all capital N. Okay. What is the meaning of OP? OP is the operator null. It's okay. It's okay. This holds for all points. It's okay. This shows a kind of the isometry, almost isometry of phi tilde nt. It's okay. Okay. Here's a remark. Okay. This inequality is weaker than this one. Okay. So if phi tilde nt, phi tilde nt is isometry, if and only if this one is equal to z, is okay. This is by definition of isometry over a map. Okay, and the operator norm is given by the highest eigenvalue of this one. It's okay, highest eigenvalue. So this condition means the highest eigenvalue of this is close to 1. Okay. But this condition means all eigenvalue is close to 1, which is different. Okay, here is a problem. Okay, I'd like to give a natural question. Okay, what happens if we replace the injected radius condition is replaced by volume condition? In my knowledge, related results about embedding problem always assumes injective radius bounded below. Because under this condition, we can control the harmonic radius. If we know the control of the harmonic radius, then the problem reduced to the Euclidean ball. Okay. But under the assumption of the lower bound of volume, then there is no lower bound of harmonic radius. So a priori we cannot, the problem is reduced to Euclidean setting. But this condition is very natural. So if we attack this question, so we have to find another new way to get some result. Okay, then I'd like to introduce an idea. Okay, well, this is use RCD theory. Okay, what is the meaning of RCD theory? Is a synthetic notion of rich bounds from below, and the dimension is bounded above by constant n. So I'd like to in my talk, I'd like to introduce an application of this RCD theory. RCD theory means a geometric analysis on non-smooth spaces is to smooth space. Okay, so I'd like to introduce the RCD space. So the authors are Storm, Roth-Villani, and Buttazzo. They introduced a CD theory and CD star theory. Then Ambrosio, Gigli, Savare, and Gigli introduced RCD spaces as follows. Here is a definition. This is a very rough definition. Okay, let us fix a metric measure space. Metric measure space. What is the meaning of metric measure space? The first M means a metric. It's okay. First meaning is metric. The first two things means a complete separable metric space. The M means a metric. The second M means a measure. Okay, measure. The Borel measure on X. In my talk, we always assume the full support. Okay, then this notion makes sense. Okay. Rich bound 0 below by K, and dimension is bounded above by N. Okay, this is so-called RCD Kn space. Then the definition is as follows. The definition consists of four conditions. Okay, 4 conditions. The first condition is a volume growth condition. The volume growth is at most this one. It's okay. The second is a Sobolev space. Sobolev space is a Hilbert space. But in general, the Sobolev space is not Hilbert space. Yeah, it's just a Banach space. Yes. So the Hilbert space condition means some linearity of the space. And the third condition is important, which is Bochner's inequality. You see, Bochner inequality. This condition is makes sense in weak sense for every nice function f. And finally, the fourth condition is Sobolev 2 Lipschitz property, which is okay. Roughly speaking, this condition means if the Sobolev function has a bounded gradient, then the function must be a Lipschitz. Okay, or more precisely, f has a Lipschitz representative. It's okay. Well, this is the definition. Okay, here is a remark. Okay, more precisely, this definition should be written as RCD star Kn spaces. Okay, by definition, RCD space is RCD star spaces. So this RCD star is a weaker notion a priori. But recently it was proved by Cavalletti-Millman. Their notion are equivalent. So to simplify my presentation, so I'd like to use RCD condition, RCD notion. Okay, here's an example of RCD spaces. Okay, this is okay. The one of them is a convex body. Convex body of Euclidean space is always with optimal Hausdorff measure. Then this is RCD spaces with non-negative Ricci curvature. More generally, all Alexander spaces. Alexander spaces is a synthetic notion of sectional curvature bounded below. Yeah, such metric spaces is also RCD spaces. And the second one is a weighted Riemannian manifold. And the third condition is their measured Gromov-Hausdorff limit. Okay. This example tells us that in general, RCD spaces has dense singularity. Okay, dense singularity. So the RCD space has very complicated in general. It's okay. So in order to introduce main result, we have to run geometric structure results follow from Gigli-Pascaletto and Mondino neighbor and recent breakthrough by Bruce Semolo. Then the statement is as follows. Let us fix metric measure space with of RCD star RCD Kn space. Then there exists a canonical Riemannian metric of the space. So I'd like to give a remark. Okay, the Riemannian metric of RCD space makes sense. But in Riemannian geometry, then the direction is opposite. That is, in Riemannian geometry, we first fix a manifold, and we next take a Riemannian metric. Then we can construct the canonical distance. Okay. In RCD setting is opposite. We first take the metric space with measure. Then we can find nice Riemannian metric, which is compatible with the distance structure. Okay, then the canonicality is defined by satisfying this inequality. Okay, the second statement is as follows. There exists a unique n. Okay, unique n. Okay, the second statement states, roughly speaking, the dimension is well defined of RCD spaces. There exists a small n such that for almost every point x, the all tangent cone at x is isometric to Euclidean space. The whose dimension is small n. And omega n, this part is a normalization factor. It is not so essential part. So the n means, roughly speaking, the dimension of the tangent space. Okay, tangent cone means a tangent space at point. But in general, there is no unique tangent cone at point. Okay. This is the key point. But almost all point, then all tangent cone is uniquely determined, and moreover is isometric to a Euclidean space. Okay, let's go to the main results of my talk. Okay, the main result are two things. Okay, the first one is the following is the RCD version of Bérard-Besson-Gall theorem. Yes, so this is a theorem A. Let us fix a RCD space, which is a compact. Okay, compact. Then the embedding phi t is also well defined, because in the definition, by definition of RCD spaces, then the heat kernel is well defined and so on. Okay. The first, the embedding map is the phi t is topological embedding in L2. Okay. In Riemannian setting, this is a smooth embedding. Smooth embedding. But this setting, this is a topological embedding. Okay. Maybe as I will explain later, this is optimal. This regularity is optimal. And the pullback Riemannian metric is also well defined. And after multiplying scaling factor, then this is this is also a Riemannian tensor. So this means that this positivity means this is a Riemannian metric. It's okay. This means a Riemannian metric, and there is a uniform upper bound. Uniform upper bound. So which means this tensor is L infinity tensor. It's okay. L infinity tensor. And the uniform bound is depending only on the curvature and the dimension. Yes.
So the phi t is the same as Besson, etc.
Sorry.
If you know that X is Riemannian, then you use Besson or you use the whole phi t.
Right. Yes. Maybe I will explain it. So then the scaling factor of this is not essential. So we can replace another suitable scaling factor. So for example, omega nt time. Yes. Okay. And moreover, the third statement is a convergence result of the pullback metric. The n is defined by the previous theorem, which is a dimension of tangent space. Okay. Then the most important point is what is the topology of this convergence. Okay. In Riemannian setting, roughly speaking, this is a C0 convergence. But in this setting, this is LP. LP. And moreover, P is finite. P is finite. That if we can take P as infinity, then this is similar to the Bérard-Besson-Gall theorem. It's okay. And moreover, in this setting, the LP convergence is sharp. So we cannot improve this condition to P equal infinity. So I will explain. Let us consider the convex body, one-dimensional convex body. It is just an interval. Okay. As I say, this is RCD space. So this is a non-negative Rich bound, and dimension is at most 1. So this is trivial. Then the corresponding Laplacian and so on is a Neumann Laplacian. So we can write down the pullback Riemannian metric explicitly. Okay, that is this one. That is this one. Well, this is a little bit complicated. But the important point is this is a continuous tensor. I don't know, this is a smooth tensor. Smooth tensor. And moreover, this tensor is infinitesimal around the boundary. It's okay. If S is 0, then this vanishes. Okay. If S is equal to 0, then this vanishes. So, and moreover, this tensor is continuous. So around 0, then this value is close to 0. It's okay. It's okay. Therefore, if we consider the corresponding L infinity norm, then this part is infinitesimal. Well, this part is infinitesimal around the boundary. So the L infinity norm of this one is bounded below by C1. So pullback metric does not converge to the original one. Okay, but our result states LP norm is converged to 0. Okay, even in this example, this is non-trivial. And moreover, we can check the inverse of phi t is not Lipschitz. The topological embedding is sharp. So we cannot improve this map to by Lipschitz embedding. It's okay. And here's a remark which gives an answer to the previous question. This is a scaling factor. That since we adapt the scaling factor as this, but this is not essential. This scaling factor can be replaced by other scaling factor. That is, if we want to the scaling factor by fxt, then if we check this condition, then we can replace this scaling factor by fxt. It's okay. Okay, then the following gives an answer to the first question, which is about the under lower bound of volume. Then what happens? The pullback metric. Okay, this is theorem B. Okay, because there are so many constants. This one. Okay. We first fix a epsilon, and we take a p, and okay, maybe I forget. Okay, it's okay. For all epsilon, then there exists I don't know, for all epsilon and for all p, then there exists t0, which is depending on this constant, and for fixed t, I forget. Okay, I forget to write p. It's okay. Well, this is I have to write the p. Okay. It is important these constants are given by a priori. And if the metric measure space satisfies the following, but important point is the reference measure is Hausdorff measure. This is the important point. Well, this is the essential point. Okay. P is added. Okay, sorry. Yeah. Well, this is the essential. Okay, then the conclusion is this. This is RCD star Kn. Kn, and diameter is bounded above by d, and the volume is bounded below by tau. Then the conclusion is this one. The pullback, this is a normalization. This is a normalized map defined by a heat kernel. Then the pullback metric satisfy this condition. Okay. So roughly speaking, most of point is an immerse point. It's okay. If we apply this theorem to manifold, then the most on point pullback metric close to the original Riemannian metric. It's okay. So this is an answer to the previous question. So this is new even for closed Riemannian manifold. Is okay. Okay, I'd like to introduce how to prove of this theorem. Okay. The first statement, in the first statement, we adopt the blow-up argument of RCD space. Okay, we fix a two Lipschitz function on X. Then we consider this value to get L2 weak convergence. Okay. The proof consists of two parts. We first prove the L2 weak convergence. Then the next L2 strong convergence. To get the L2 weak convergence, we have to consider this value. Then by definition of the pullback metric, then it is equal to this one. Okay. Then let us focus this part. This part. This part. For fixed y, then letting t goes to 0, then this part localized to y be a Gaussian estimate of heat kernel. Therefore, by taking the limit t goes to 0, then for almost y, then we can calculate of this integral. Then the conclusion is this one. What is p hat? The p hat is a heat kernel of the rescaled Euclidean space, which is appeared in the tangent space at a regular point. Regular point. And the next mysterious point is what is phi I? What is phi I? The phi I is, roughly speaking, is a derivative of y, f, at y. Okay. So that is a linear function on the tangent space at y. Okay. But almost all points, the tangent space is isometric to Euclidean. And so the derivative is a linear function on the tangent space. But linear function on Euclidean space is just linear. And moreover, the gradient vector field of the function is parallel. Okay, parallel. So this value is equal to this one. It's okay. So that is, this value that depends only on n and the norm of this one, hy nabla fy. It's okay. Because this vector field is a parallel vector field. And moreover, by proving the L-unity bound via another way, then we conclude LP weak convergence. It's okay. In order to improve this to LP strong, then we have to do more delicate blow-up argument. Then we conclude LP strong convergence. It's okay. So this is a sketch of the proof of Bellard-Besson-Garo theorem in non-smooth setting. It's okay. Okay, finally, I'd like to introduce the proof of the quantitative version of the Bellard-Besson-Garo theorem. Okay, then the proof is done by contradiction. Okay, that contradiction. This is the key point. So we cannot write down each constant explicitly. It's okay. Okay, then the proof is done by contradiction. This is a new point. If not, we can find a sequence of RCD n spaces, and we can find a sequence of time, and we can find the sequence of the upper bound of embedding dimension, and where the Ti inverse is very smaller than Ni, but it's a very big one. And moreover, there exists some uniform epsilon 0. Then these three conditions hold. This is just this comes from an assumption of contradiction. Is okay. So from now on, we'd like to prove the contradiction. Okay, how to get a contradiction? Okay, we first take the with no loss of generality via Jiggly-Phillips works on non-collapsed spaces. That is, with no loss of generality, we can take the limit of the sum space, which is the metric measure spaces. It's okay. Okay. Their work allows us to take a limit. Okay, let us return to our setting. Then it is not difficult to prove that the second part of this one is L2 strongly converges to the limit Riemannian metric. It's not so hard. But the most difficult part is the first term. We can prove that it is also converges to the limit. It's okay. Then, of course, this value is converges to 0. It's okay. Well, this is a contradiction. It's okay. Okay. So why it is difficult to prove the first part convergence? Okay, to get the L2 strong convergence, then we need two things. Two things. Okay, I'd like to emphasize that if we consider the fixed space, because this setting is in the setting of the convergence sequence. If the sequence consists of one metric measure space, then the corresponding result is a direct consequence of theorem A without non-collapse assumption. But this statement is stated by measured Gromov-Hausdorff convergence sequence. This is a very difficult part. Okay, the first thing we need to use a Reifenberg property. Okay, Reifenberg property means roughly speaking, for such spaces we fix a point over the space. That if the space is a regular point, then all point near the point is also almost regular point. Is okay. Well, this is a very specialty in non-collapse setting. This is done by using Bishop inequality and Bishop-Gromov inequality and their rigidity. Okay. And moreover, by proving quantitative version of theorem A. Or theorem A is a blow-up argument, but after taking care of the proof, then we can also prove the quantitative version of this one. By combining this property, then we can prove quantitative pullback convergence result. Okay, thank you very much for your kind attention.
Thank you very much.
Thank you very much.
Questions, comments? Okay, it seems there is no question or comment, so let's thank Shouhei again.
Thanks.
To lower my voice. It's the first time somebody asked for It's a real pleasure being here in Pisa. It's such a wonderful place because for me I think it's a 9th edition, but it's more than that. We are experiencing live the success of the school, Italian analysis school, which really is happening here at Pisa. And I'm not talking only about Alessio Sfismel, I'm talking about all these young people, young speakers that I see. Most of them I don't even know, but maybe you are growing young Alessios for the next few years. So it's really a remarkable achievement. So I'll be talking about, this is a title. It's a joint work with Young Han Kim that you know from the mass transport community. He's a colleague at UBC. Aaron Palmer, he's a postdoc of mine, and he's an extremely strong person. Hopefully he will be coming to Pisa 2 years from now in the next edition. So the first 2 pictures on the left are mass transport as seen in Canada. In Pisa, I don't think this is how you imagine mass transport. You don't shovel snow. You're moving snow from measure mu to measure nu, and optimally. I don't need to explain this much. On the right-hand side, maybe it's a bit novel to some of you in this audience, which this time, instead of what you have a source, which is like a sprinkler, and diffusing water in a random way, and this is a source measure mu, and then the water stream stops somewhere when it hits a barrier, and this is, you see, this is a Brownian motion stopped at time tau, and this is a distribution of Brownian motion stopped at tau, and the barrier, and the stopping time is the first time this water hits this barrier, which are the flowers. So there are 2 different ways of mapping a measure to another, and they look very different. But what I'm trying to, and I try to show you that actually they're all the same phenomena, and there are 2 now I need to, okay. And these are only two examples of really generalized phenomena. You know, how to move a measure mu to a measure nu. Here you know about mass transport, and mass transport has given lots of techniques. But actually, this is the statisticians, the geometers, analysts, potential theorists, always deal with correlation between two measures, mu and u. And you'll be surprised, you've seen them maybe in various things, how all of them, what do they have in common? They're all essentially, they're very similar to mass transport, even though they're not. And I'm giving you just some examples. I wrote a paper about this with a student of mine, Malcolm Bowles, who is looking for a postdoc, by the way, if you have any position to spare. And so these are the examples that mass transport, you all know about it. This is a correlation between two measures. But there's another one which is much more classical, which is a balayage theory, which is when you have a measure and then you diffuse it toward the boundary. This is Shouhei theory. In the old days, we used to call it Shouhei tree. And then we have martingale transport, I'll be talking about it now, which is essentially balayage theory with a cost. And then you have optimal Skorokhod embeddings, which I'll be talking about today. But then you have the stochastic mass transport by Mikati and Thiolin, where so they're not associated to a cost going from, because processes do not go from one point x to one point y, but they're also fit in this theory of correlating two measures. Brownian bridge, I see that the master of the bridge, the first one who crossed the bridge is Leonard, who's here. Weak transport, which are also introduced by Talleyrand, Martin, and Ghoussoub, also fits. Even the logarithmic entropy, field planning problems that I saw recently by Savary and his collaborators, they also fit in this theory, and Fisher-Jones-Verdin. All of them are correlating measures, but most of them, besides the first one, are not mass transport, yet they enjoy the duality, and the other amazing techniques that you developed in mass transport can apply to the other areas with lots of nice results. And I call this a theory of transfers because it contains all this. There's one definition where all these things are just examples of this theory of transfer. It's a really mass transfers as opposed to transport. I will not be talking about all of them. I will be talking only about the two examples that I mentioned at the beginning. But this is a paper on arXiv. Please take a look, because it's really mostly examples of how do they fit in this one concept. Okay, now, so you know, I don't need to explain the Monge definition for mass transport, where C is a cost going from X to Y, and then you have the Kontorovich formulation, which is about given this way. I'm going to talk about the probabilistic interpretation, which is another way to define this problem, which is the expectation of the cost of going from a random variable x to a random variable y. So over all possible joint distribution, when x is the distribution of x is mu, the distribution of y is nu. So this is handy for me to talk about it probabilistically. Because what? Why is this thing? Okay. Because I want to talk about martingale transport. Now, martingale transport are exactly like mass transport. They look like it. You have joint distribution. The only difference is that here x and y are correlated. The conditional expectation of y, knowing x, is x. So it's a martingale. The pair xy form a martingale in a probabilistic way. So one-step martingale. Same definition, okay, but now you are constrained in terms of your selection. Now, for the analysts, you are used to this definition of mass transport when you have pi, which is a measure on the product space, okay? So the additional constraint here is that when you have pi and you disintegrate with respect to mu, so you have pi x for each x, a measure on y for each x. So for pi to be a martingale, you need the barycenter of pi x to be x. So the new constraint is that the barycenter of this disintegration at pi x is x. Okay, so x is really on the diagonal. Now, we don't have necessarily martingale plans, martingale transport from measure mu to nu. There is necessary and sufficient condition for this set of martingale transfer to be non-empty is that mu and nu be in convex order. Now, what's a convex order? That mu precedes nu according to the cone of convex function C. If whenever you hit it with a convex function, then you have this inequality. So really, there's an order. So you could see already that mass transport is too symmetric. The martingale transfer already has one direction. You're going from mu to nu. Okay, so already you have to, and the theory of transfer really doesn't specify a direction, not just. So this is the definition of martingale transport. And duality, which is the most important aspect of mass transport, is the control-which duality, as you know. The infimum here is the supremum over when you decouple C. Decouple C, that means you take all functions psi and phi, such that psi of phi minus phi of x less than C, and you integrate d pi. But now, since marginals are nu and mu, and pi is, and psi and phi depend only on one variable, then you have this duality. So, and the optimal transport, when it exists, it's supported on this set where C is equal to psi minus phi, and this is where all the analysis come from this important thing. Now, for martingale transport, what happened? You have an extra constraint on the primal problem. So on the dual problem, you have an extra degree of freedom. And so you have exactly the same thing for the duality for martingale transport, integral of psi, phi. But now you have psi and phi. You have an extra constraint here. They're not just below C, but you have to add this linear perturbation here, such that if you integrate d pi, if you integrate this, d pi is 0. Okay, so this corresponds to the constraint, the martingale constraint. So you have an additional freedom for the dual problem. And then again, if phi is attained, phi and psi, then you have to work on this thing. So the first problem with mass transport is a dual problem attained. Usually the initial problem attained is easily, at least in terms of if you don't care about having a graph, it's easy for mass transport attainment usually, and then some kind of regularity that you get very easily if the cost function is Lipschitz. This is where the theories start differing. It's much harder to prove duality, attainment of duality for martingale transport. First, it's not true in general. For example, if you take the cost to be minus distance x minus y, and you minimize, the duality is not attained. This is an example by Balogh and Juillet. Even in one dimension. So we don't have attainment in general. Now, we worked on this problem with Kim and Lim a couple of years ago, and we managed to split the problem, to disintegrate a martingale problem into a disjoint components of martingale problem, such that on each component the duality is attained. So this is, I think, a substantial piece of work. The problem is, so we can split the problem into, the problem is that if you're not in one dimension, then the partition or disintegration is non-countable. And because of that, you cannot control, if you start with an absolutely continuous measure, you cannot control whether a measure is, when you restrict it to disintegrate, whether it's absolutely continuous. And there is a counterexample by Luigi and colleagues that gives you a counterexample that you really cannot decompose in an absolutely continuous way. So all what we managed to do, we proved it in 2 dimensions. 2 dimension, you don't have much room, right? So you could prove that you have this kind of duality up to a decomposition in 2 dimensions. So the problem about attainment of duality in higher dimension is totally open. Okay? In 1 dimension, there's lots of problems. Actually, the people in math finance are the one who started. All these people who do math finance, do martingale in one dimension. So big problem, a higher dimensional martingale transport problem. What can you say about the structure of the optimal martingale and when the duality is attained, or at least modulo up to a reducible component? So this is a very open problem, only known for dimension 2 so far, and non-trivially. So I think I skipped something here. Another aspect of mass transport is, suppose the cost is given by a Lagrangian. So the running cost is really given by a generating function of a Lagrangian L over all possible paths going from Y to Z. Then this allows you to introduce a Eulerian formulation, which is this time, it's in a way you linearize the problem. That's eta, L is Lagrangian, but then you are minimizing over possible etas, which are defined on measures on phase space, and eta starts at mu, ends at nu, and verifies the continuity equation that you've already heard about it today. Okay, so this is another aspect of mass transport that I would like to see what is a version for martingale transport. Okay, so I know, and some people here, organizer, who worked on Benamou-Brenier, but there are many aspects of Benamou-Brenier for mass transport, many formulation for this. Okay, so why there's a problem in high dimension? Because in one dimension, all the martingales are the same. They're all Brownian motion. All of them are embeddable in Brownian motion in a certain way. In higher dimension, you have different kind of martingale. You have the general martingales, which they can split in 2 points, and then the next ones can split in a disk, and then the next one can go into a ball. So the dimensional analysis of the support of martingales in general in high dimension can be very complicated. That's why we cannot solve it for dimension bigger than 2. But you have different kinds of martingales. If you restrict yourself, for example, to subharmonic martingales, these are the Brownian martingales. These are the ones that really develop in bubbles. Or plurisubharmonic martingales. These are the ones that develop in 2-dimensional disks. Then maybe you can get a structural result. And that's the beginning of my talk. So I'm going to So I want to deal with subharmonic martingales in a higher dimension. So what is the key theorem here? It started by Skorokhod. Okay, and then zillions of people worked on it. So if you have 2 measures, but this time in subharmonic order, notice that it's the same order, but now it's true not just for convex function, but it's true also for subharmonic functions, which is a larger class. Okay, so it's a stricter. It is a stricter, more restricted definition for the measures. So here, what's amazing, the theorem of Skorokhod, which is done in 1 dimension, but it's true in higher dimension, then you can realize measures mu and u by Brownian motion. That means you can start Brownian motion at mu, and then you can stop it in such a way that the distribution of the final stopping time is nu. So if you take subharmonic martingales, you can just embed them in Brownian motion, okay, as initial state of Brownian motion, and then final state of Brownian motion, but modulo is stopping time. So, okay? So these are very special martingales in higher dimension. And these are the one that I want to say that we can say something about, is the subharmonic martingale. So remember what is the optimal subharmonic martingale problem? That means if you have expectation of C of x, y, where distribution of x is mu, distribution of y is nu. Now, because of Skorokhod embedding, it reduces to studying this, the minimized expectation of the cost between the initial state of Brownian motion and final state of Brownian motion, that means stop Brownian motion, according to this. So this problem, the optimal sub-Riemannian problem, becomes a problem about stopping Brownian motion. So instead of looking over all possible martingale plans, now the problem is minimizing over all possible stopping times. Okay, so you change the problem completely to a problem stopping times. So this is the optimal Skorokhod problem. And there are many constructions of optimal stopping time or of stopping times that realize mu and nu. Many constructions started by all these people. So here, for mass transport, you take it for granted that there's always a measure whose marginals in mu and nu. Here, you don't take it for granted. To prove that there exists stopping times that realize mu and nu is already a construction, and there's about 28 constructions known so far. But here, what we're going to do, we're going to assume that these constructions exist. Actually, there's a convex compact set of stopping times. These are called the randomized stopping times. And what we would like to do is, remember, I want to minimize the expectation of this, of the cost between the first time and the final time. But also, we can also take the Lagrangian here of Brownian motion, and between 0 and t, this can be a cost. So, and I want to minimize the expectation of this. So let's take any stochastic process st. So this will be the cost. So now, among all possible realization of mu and u, I'm gonna take the cost of stopping at tau. S is a given cost. So now the cost is a process, stochastic process, right? So we started. I mean, this is really the one that's the closest to what you know, the cost of going from initial state to stopped state. But we just take any stochastic process. So this will be the what I call the optimal Skorokhod embedding problem. Okay, minimizes. So what does it mean? This time, it is an optimal transport problem in a way, but now the transport of mu to nu can happen only along Brownian path. Okay, so you are restricted in terms of the way to get from one measure to a measure nu. So this is how one way to see it. And let me give you some analogy. This S is a stochastic process, and this is the expectation of S tau. But S tau, what do I mean by a randomized stopping time? Now, stopping time is for every path, omega, you have a certain time t, right? Usually it's a graph from omega to the positive reals. So it's a graph. But we cannot always find a true stopping time that realizes a measure nu. So what you do, the probabilists did a trick which is like Kontorovich a long time ago. They introduced randomized stopper times. So instead of taking graphs from omega into the reals, they take a product measures on omega across the reals. Okay, so if you disintegrate, this means that for every omega you have a distribution mu omega on R plus. So you replace the graphs by distributions whose first marginal is the is a probability underlying probability space. Okay, so in a way it's very similar to Kontorovich convexification and. Okay, so when I talk about stopping time, it's really a randomized stopping time. But again, the final analysis, you would like to get a true, honest to goodness stopping time, and you would like to characterize it. Okay, you would like to really. Okay, super martingale. Super martingale. It's a real value. Super martingale is it verifies this property that. Okay, so it's. I need this. So you have an adapted sequence or adapted family of random variables GT, and it's a super martingale. It's a conditional expectation of GS at time ft is less than GT. Okay, so it's expectation are decreasing. That's the definition of super martingale. And now I want to give you one theorem by Biegelbach, Cox, and Hussmann. Just I think appeared in Invenzioni recently. They considered exactly this problem for the same reasons I gave you. They're the one who started this analogy with mass transport. And you say you take any stochastic process adapted to the Brownian filtration, let's say, and you minimize this, then you can prove a duality, just like Kontorovich. But what does the duality say? Instead of having two functions psi and phi, you have one function psi, and you have here a stochastic process G, which is a super martingale. Okay? So you are maximizing over dual pair. The pair is one function and a super martingale. And here, this is you integrate psi nu. This is the final measure. Here, expectation of G naught is really you are integrating with respect to the initial measure. It's the same thing. G naught is the beginning of the super martingale G. And what are the conditions? ST is a stochastic process. GT is this super martingale. Here you have this function psi applied to Brownian motion. So that's a process. My GT is less than ST. If you take all possible psi and G verifying this, then this is a dual problem. And then they show that if the dual is attained, it's a big if, on G star psi star, then tau is optimal. You can find the optimal stopping time. It will be the first time where this thing is a martingale, where the super martingale is a martingale. Okay, up to time tau. So in a way, this is a characterization of the stopping time that solves the problem. Okay, and then you have equality, just like the Kontorovich. Okay, you have equality between this and this. So this is what they prove. The problem is that they're not even close to proving attainment, that this G star, psi star exists. And this is where our work started. When can we have attainment? Because we were working on a more specific problem where this S tau is a Monge distance between initial Brownian motion and final Brownian motion, right? But let's say, okay, let's take a look at this stochastic process. Maybe we can give us an idea. And sure enough, it turned out, and as I said, there's never an attainment, like in this example. Sometimes we have cost with you, and there's no attainment. So it means you have to have an extra condition. And we worked out the case when you have a Lagrangian. If the stochastic process is integral between 0 and t of a Lagrangian of Brownian motion, depends only on state, notice here. Then we proved that we need L to be positive, the Lagrangian to be positive. In other words, this ST is an increasing process. So already that's an extra assumption on the cost. So it's not any stochastic process that like in the work of Cox and Hughes, right? We need to be. But then when we looked at our problem, which is a norm between initial Brownian motion and W2, then here you have a norm. So it's not an increasing process, but it is subharmonic in the second variable. So in the first case, ST was increasing. In the second case, if C is subharmonic, ST is a submartingale. Okay, it's increasing in expectations. So these are the two ideas, the two examples we have in mind. This tells us really that if you want to prove any existence, attainment, then the cost function should be the process should be a submartingale. And this is what we prove. Okay, so let me see. So there are 3 ways how we can improve. So, you know, you have a pair, psi and g. What you do in the mass transport is really reduce it to only one problem, psi. Because if psi is fixed, you have the best phi that for which the duality. This is a C-concavication, right, procedure. Here we have something similar, which is really given by the Snell envelope. Snell envelope is a procedure where when to stop if you're gambling, okay? How to gamble if you must. So when is the stopping time to say, okay, that's it. This is this process. So if you have a process, psi, and it amounts to finding the lowest supermartingale above it. This is a Snell envelope in probability, which is exactly what we do here. You take psi is given, and you would like to find this optimal G. This amount is a C-concavication. So you take psi minus the cost, psi of Brownian motion minus the cost, and you take the Snell envelope, usually is defined like this. So that's how you find your supermartingale. So you find the smallest supermartingale above psi minus st. So this is equivalent to the C-concavication process. Okay? So if you have psi, you can find the process G. But in this case, the dual problem is equivalent to finding the supremum of this. So really, you have only one variable, which is psi, because G psi is just the Snell envelope. So now it's an upper continuous concave function. So it's easy to maximize this in psi, because it's concave in psi. The problem is that you want to find the right topology. Okay, you want to find the right topology for psi for the dual to be attained. So what do we do? As we said here, the problem is that we have an additional degree of freedom, and here it is. See, if you take psi and you remove from it a harmonic function, h, and then you take the supermartingale and you remove from it a harmonic function of Brownian motion, then nothing changes. It's like in the regular mass transport, if you remove a constant from psi and the same constant from psi, nothing changes. So up to a constant. So you can gain by just subtracting a constant, right? You can in some bound. So this is really the beginning of the analysis. What's nice about it is that it doesn't need to be harmonic, h. You don't need to remove the harmonic part, but you can remove a superharmonic part as long as it is the smallest superharmonic function above psi. So here you have one. So if S is a submartingale cost, then what you can do, you take psi, you remove from it its smallest superharmonic function above it, and then for G psi, you remove from it, this should be psi bar of Brownian motion. Okay? So not only you can remove harmonic functions, but you can remove a smallest superharmonic function above psi. But this is amazing, because then if you remove from psi the smallest superharmonic function above it, then you can restrict yourself to psi less than 0, right? You remove its envelope. Now you restrict yourself to psi less than 0, and also you force yourself to have a Dirichlet boundary condition. So that's the first estimate. So you get an affinity estimate on psi by just removing the smallest superharmonic function above it. The same thing as when you prove regular attainment for a dual function by removing the constant, an infinity norm. Okay, but now, so you have 3 ways to improve the maximizing pair, if you will. One way is you take psi and you remove its superharmonic envelope. Okay, so if psi is given, you can improve it like this, and then it becomes less than 0. Now, if G is given, the supermartingale, you can improve psi by taking this, the supreme over phi. So this is essentially like the concavication. Okay, so if psi is given, you can improve supermartingale. If supermartingale is given, you can improve psi. So you can, and then if you have psi, you get the Snell envelope. So you have three ways of improving a pair. And you use them, you iterate them, and then you get these estimates. So if the cost function is bounded like this by k, if the expectation of a style, then psi is you have an L-infinity bound. Okay? So you have an L-infinity bound, so you can have a weak star convergence. So you have an attainment of duality. The problem is your functions are on L-infinity, defined almost everywhere, it doesn't get you anywhere. So you really need a better regularity. But to get better regularity, you need an extra assumption, which is this, on the cost function. So if the cost function is Lipschitz this way, then you can have an assumption, you can prove something on the Laplacian of psi. So the first time we use Sobolev estimate to prove that the duality exists, the dual attainment exists, to have energy estimates. Okay? So for our examples, if L is bounded, is between 0 and D, then you can have an energy estimate. And that's what you need here for the, in the case you have C. So under these assumptions, we could prove attainment. But attainment in Sobolev space, and therefore you have nice regularity. So this is a result with came in that, for example, in the case of the Lagrangian, let me just talk about the case of the Lagrangian because I want to do some dynamics. Then the dual problem is attained and attained in a Sobolev class. And then in case of the cost function is given by Lagrangian, look, you don't need to talk about the supermartingale anymore. You can talk about another function. So now it's exactly like in mass transport. You have psi and j. So if psi is given, the supermartingale is given by a function j corrected by the Lagrangian, and the function you can write it as is. Okay, so you can find two functions, psi and j, for the dual problem. Okay, so that's the first result. Again, if the cost is a submartingale, you have duality is attained in the Sobolev class, and therefore you have regularity, and you can do things with it. I want to talk about the Eulerian formulation because that's another element, a new element here. Usually, what you do when you do the Eulerian formulation or Brenier-Benhamou, if you will, you just take the distribution. Okay, this is eta, so there exists an eta that corresponds to the evolution before the stopping time tau. So you can associate eta, but here there's something new. Here there's a distribution to the stopping time. So when you stop at tau, there's a distribution in rho, which is what we call it the exit or the stopping distribution. So for the Eulerian formulation, you have two flows now. One before time tau and one at time tau that you want to deal with. So what is really the equation that replaces the continuity equation? So rho is a stopping measure. It's a distribution of tau and w tau. So, but when you work out what this means, this time, the evolution equation is, look, in the classical case, forget about rho. Rho doesn't exist. This is the exit distribution. You have d eta dt. This is a heat equation. Now, why do you get only the heat equation? You don't have the advection current. You don't have the velocity term. Because the Lagrangian, in our problem, the Lagrangian only depends on the state L of wt. I did not have a Lagrangian depending on I don't have a drift. I don't have a, okay? velocity. So really, it's just a heat equation. But here, in this case, I have two variables, eta and rho. Eta starts at mu, and rho, between 0 and infinity, it's nu. Okay, so it's really, you don't have conservation of math, right? Because the math is dropped, right? And only when you attain the stopping time that you finish the process. So it's a new kind of continuity equation. So you can prove that the problem is, so you have an Eulerian formulation, which is this. This is the same as before, as a mass transport. You have L and eta. Remember L here, because it's L of depend only on the state. We don't say there's no dependence on the velocity. I'll talk about dependence on the velocity later. But subject to eta satisfying this heat equation with a rho here, okay, and eta starting at mu, and this and rho is a distribution. Total distribution of is nu. So this is Eulerian formulation, which is really different from the mass transport case. I think it's very important, a new point of view with this Eulerian formulation, with a stopping, with an exit measure. Now, for this, you can prove a dual problem. Remember, all these are the same problems, but different formulations. Now you have a dual problem, which is psi, as usual, but here you have j, a function would depend on time, and j satisfies this equation, which is a Hamilton-Jacobi equation. Okay, this is a Hamilton-Jacobi equation for j, but only before j hits psi. When you have a fixed time, when you have fixed end time, you have psi of x, which is a final variable, and then you solve the Hamilton-Jacobi equation backward, right? When fixed time. But here time is not fixed. So you have psi, you know that the process ends at psi, but you don't know when. So it's really an obstacle problem. It's a so really if j, so you'd like to solve the minimum of this is equal to 0, right? Okay, so if j is not equal to psi, then you are solving a regular Hamilton-Jacobi equation. Okay, this is just a Hamilton-Jacobi. It's second order because you have the Brownian motion. Here I better hurry. So really becomes you can prove j using probabilistically. So you are really trying to solve viscosity solution for this kind of Hamilton-Jacobi inequalities as opposed to equalities. And again, you can prove that this exists. Now, how do you want to prove what is the stopping time? Once you find psi and j, you find the space-time Tx where j and psi are the same. Remember, j is evolved in time until it hits psi, but we don't know. Okay, so this is the barrier. So really, these are given by duality, psi and j. But when j hits psi, this is really where the process stops. And because it's a barrier, you can define s of x to be the first time j hits psi or the last time, depending on the Lagrangian, whether restricting, increasing, restricting, decreasing. So, and this is how you can find exactly the optimal stopping time. So the duality gives you two functions, psi and j. One is time dependent one, and then it's an obstacle problem. And the first time you hit the obstacle is exactly the stopping time. So it's not even probability anymore. It's as PDE as can be. Okay, so all these constructions of stopping times that are done by hand by probabilists, this is just it's an obstacle problem given by a variation inequality, which is really beautiful and simple in a way. Okay, but here also you see how the evolution of eta happens. So there's connection between PDE, variation inequality, obstacle problems, mass transport. It's really a nice combination of many kinds of mathematics. This has, for example, this is a barrier in both cases where the capital L is strictly increasing or decreasing in U. This is a Brownian motion, and then tells you how it hits. This is how you can find the optimal stopping time. Now, what happened is, what happened if you really we want to deal with a norm between W0 and WT? This turned out to be, because it's singular at 0, right? Because you want the Laplacian to be bounded. But if you take the norm to power 3, you're fine. But if you take the norm, then you have singularity at 0. So this doesn't apply. So we had to do some different, much more delicate analysis to prove this case, which is not written yet. Okay, so this case, which turned out to be so this is a Monge analog of, this is a Monge martingale problem analog to Monge, and this is much more delicate. It has delicate regularity problem. I want to talk about, okay, extension of this problem. Notice that here I had L and Brownian motion in my cost, but actually you can do X is a solution of stochastic PDE, dx equal Vt dw, and the Lagrangian can depend on X and on the drift Vt. Okay, and then in X naught, so you can do the same thing, and you can prove a duality. And here, look, in this case now, because you have Lagrange depend on the drift, now you have here you can see the continuity, the Hamilton-Jacobi equation. You can see this, the second order, because you are doing the diffusion, and then this is L. But this time, as I said, it's an obstacle problem. It's not a Hamilton-Jacobi equation. It's Hamilton-Jacobi inequality. And the first time you hit is a solution for this. And more than this, see, the Eulerian formulation that I showed you is linear. It's usually L times eta, provided eta satisfies Fokker-Planck or right. But here you can extend this to a much more general situation. You have the Lagrangian here, L times eta, so it's linear eta, but you can add a term f of a convex function of eta. And I think that Brenier, in one of his talks that I saw online, he dealt with this kind of problem f, and I think also Savary and when you talk about, so you dealt with L eta plus f of eta. But then here, because it's a stopping time, then you can add a term, and rho is the exit measure. Rho is a stop measure. So this is really a much more general problem that's relevant to mean field equation. But and then again, subject to the Fokker-Planck equation, rho is a stop measure, and the rest is what you know in terms of it's a continuity equation with a drift, and then again here you have to solve another Hamilton-Jacobi inequality. But here, notice here the difference on the right-hand side. It's not 0 anymore. It's really G prime that comes from this term. So it becomes more complicated. But the setting is, I give you this Brownian motion setting because it's very, very simple and intuitive, but it can extend to, but then it reduces all these problems to really just Hamilton-Jacobi inequalities. And I think I'm done. Thank you very much. Thank you, Nassif. Is there any question? Yeah. Microphone? What?
Okay. When you when you move from Lagrangian to Euclidean related equation, do you have an abstract equivalence also in your paper? Or
do I have what?
You moved from the probabilistic description to the PDE, right?
Yeah.
You just moved. You said the Brownian motion satisfies the Ito formula and so on. Can you also go backward? Say if you solve the PDE formulation, then you solve.
Yes, they're equivalent. I mean, the Eulerian. Yes, exactly. You go from Eulerian to the regular and then back and forth, and the infimum are equal, and then each one of them have a different dual problem. One with the super martingale that I showed you, and one with Hamilton-Jacobi inequalities, and all of them are the same. The four formulas are the same. But I think what's new for PDers and is really we have this new term, is this exit measure, the stopping measure that adds to the continuity equation. It's not any more conservation, and then I think this has to be analyzed by the experts. It's a totally new idea.
Any other question? So let's thank Nassif again.
Thank you.
Okay, let's go to the second talk in the afternoon by Luca Tamanini from Bonn.
Yes.
He will speak about variational representation of the Schrödinger problem and applications.
Okay. Thank you. Thank you very much for the introduction and for the invitation. It is my first time here as a speaker, but third time as a participant. And in these years, I saw that the interest towards the Schrödinger problem has increased a lot. And indeed, and I saw that this week there will be several talks on more or less related subjects. Hence, I'm happy also to be the first one and to start with to have the opportunity to talk about variational representation of such a problem, because for those of you who are not familiar with it, this is a good starting point, as it allows to understand the strong connection and analogy and also differences between Schrödinger problem and optimal transport. So let us start with by describing the structure of the talk. In the first part, I will resume the most famous representation formulas for Wasserstein distance, namely Benamou-Brenier formula, Hamilton-Jacobi and hope-flux duality. Then in the second part, I will introduce the Schrödinger problem, spending also some words about regularity features of the entropic interpolation. And building on top of this, in the third part, I will see how the picture we had in the first part holds true also with some adaptation for the Schrödinger problem. This third part is based on a joint work with Nicola Gigli. And in the last part, I will give you an introduction, an application of one of these variational representation in the context of in the study of long-time behavior of entropic interpolation. And this last part is based on a work in progress with Giovanni Conforti. So let us start by optimal transport. So, well, the first slide does not require any comment. I think it's just a standard definition of Wasserstein distance in the Euclidean case. Let me just point out that with this definition we have a static picture, because we do not look at we do not care about in which way the mass is transported from mu0. I mean, we do not look at the time evolution of the mass between mu0 and mu1. We just have the initial and final configuration and a transport plan between them. The dynamical interpretation comes into play when one talks about the Benamou-Brenier formula. This is indeed one of the biggest achievements in the study of optimal transport, as it allows to see the transport of mass in a dynamical way, and actually as a minimization problem of this of the kinetic energy associated to a solution of the continuity equation. Where here, by continuity equation, as one can expect, I mean a distributional solution of the continuity equation with integrable vector velocity field and bounded compression assumption. Then one can pass from this dynamical point of view to a dual one by observing that, okay, now let me say also one thing more, that we can actually say something about the minimizers of this variational problem. Indeed, the minimum is achieved if and only if mu t is a Wasserstein geodesic, in the sense that it has a constant metric speed, and the velocity field is uniquely determined. So, as I was saying before, we can pass from this dynamical perspective to a dual one by observing that the continuity equation is in duality with the Hamilton-Jacobi, in this sense, that if we have a subsolution of the Hamilton-Jacobi equation and a solution of the continuity equation, then this inequality holds true, and this leads us to this result by Othon-Villani and Bobkov-Gentil-Ledoux. Then one can observe that in this supremum it is not restrictive to consider only solutions of the Hamilton-Jacobi equation, and for viscosity solution of such equation we have an explicit representation given by Hopf-Flachs semigroup. I recall its definition, so that the previous variational formula for Wasserstein distance becomes this one. And by the very definition of Hopf-Flachs semigroup, we recover the standard Kantorovich duality. So to sum up, we have a very rich picture of very different ways to represent Wasserstein distance, and that allows us to attack optimal transport with tools coming from PDE rather than convex analysis or standard duality argument. So far I just stated everything in Rn, but of course these results have been generalized on general metric measure spaces, for in particular RCD-K infinity spaces. Indeed, the Benamou-Brenier formula was proved by Gigi and Han, the Hamilton-Jacobi duality by Cuvada and Gigi Cuvada-Ota, and the Hopf-Flachs duality independently by Ambrosio, Gigi Savaret, and Gosselin, Roberto, Samson. Okay, this is all for the reminder part. Let us now move to the Schrödinger problem. And since optimal transport, as we have just seen, can be represented in many different ways, also in abstract framework, this can be shown. This is also the case for Schrödinger problem. So let us make our framework precise. For those of you who are not familiar with RCD spaces, from now on, the triple XDM can be a smooth Riemannian manifold with bounded Ricci and the bounded dimension, or a weighted Riemannian manifold equipped with a probability measure where the weight satisfies this natural condition. But as I was saying, as one can expect, it can also be an RCD star Kn space, as it was defined this morning by Honda, or an RCD K infinity space equipped with a probability measure. With this said, let me now introduce the Schrödinger problem. Of course, it can be defined in different ways depending also on the application that one has in mind, but I would like to start with by quoting Schrödinger himself. So his 1931 paper, über die Umkehrung der Naturgesetze, so on the reversibility of nature laws. In this paper, he was motivated by finding an example within classical mechanics that explains the equation named after him. So a Euclidean example for the quantum mechanics. So he suggested this situation. Assume that we have a particle whose trajectory is a Brownian motion, and we assign an initial law W0 for the particle, and we also assign a final distribution at the time t1. And we want to, given these two laws, we want to determine the law of the probability distribution of our particle for intermediate times. In other words, assume that, as is said here, we do two observations at the time t0 and the time t1. So this is the question: which probabilistic statement can we deduce from our two observations on the intermediate observation? And since omega 0 and omega 1 are arbitrary functions, and our particle moves as a Brownian motion, this means that we are conditioning on some unlikely event. In the case omega 1 is not the evolution of omega 0 of W0 by the heat flow. So from a physical point of view, this means that at time t1 we observed something improbable but still possible, and knowing that, we want to find how the particle arrived to such an unlikely event. Schrödinger, in his paper, of course, then generalized this problem from 1 to n particles, and then using combinatorics and Stirling expansion, passed to the case of continuous distribution. So in the end, we have this problem. So given two probability densities, we want to factorize them. So we want to find two suitable functions f and g such that these identities hold, where P1 is the heat semigroup at time 1. If we are able to do so, then the answer to the previous question is given by this definition. So this is how the entropic interpolation is defined, and this is how our particle, particle system moved from an initial configuration to an unlikely final one. In this picture, we can also introduce a slowing down parameter epsilon that appears in the Schrödinger system at the level of the heat semigroup, and determines also the definition of the entropic interpolation as we slow down once more the heat semigroup here and here. Of course, life of physicists is a bit easier, as in his paper, Schrödinger gave for free the existence and uniqueness of the function f epsilon g epsilon. The point is that such existence was proved only 30-40 years later. And the idea is the following. So if we define measure r epsilon on x times x, which is given by our reference measure time itself weighted with the heat kernel at time epsilon, then a first observation is that the couple f epsilon g epsilon solving the Schrödinger system, it actually solves the Schrödinger system if and only if this is a transport plan from rho 0 to rho 1. So we translated the Schrödinger system into a transport problem. And a second key observation is that there exists only one transport plan of such a form, and it is characterized as the unique minimum of this minimization problem, which is what is now called Schrödinger problem, even if it was, let's say, rediscovered in the 70s by Jamison, in 75 actually. The existence and uniqueness of minimizer for such a problem follows by standard methods in calculus of variation. The fact that this the minimizer of such a problem has the desired factorized density follows by looking at its Euler equation, which is this one, which forces the logarithm of the Radon-Nikodym derivative of the minimizer to be decomposable as a sum of two functions, so that now it is sufficient to take the exponential of such functions to get our desired f epsilon g epsilon. So as far as one is concerned with just existence results, existence actually holds under rather general assumption, but if one wants better properties for f epsilon g epsilon, one has to add, for instance, this condition, And for this reason, we restrict ourselves to RCD-KN spaces or RCD-K infinity spaces with a probability measure, as this is nothing but, this is equivalent to a lower control on the heat kernel, which is known to be true on RCD-KN spaces by Jiangli and Zhang, and in the case of finite dimensional RCD spaces, and by Ambrosio, Gigi, Savaret in the case of RCD-K infinity spaces with a probability measure. So under this assumption and the fact that ρ0, ρ1 has bounded support and densities, and observing also that the function f epsilon has to be the same support of ρ0 and the same with g epsilon and ρ1, one deduces that f epsilon is integrable, and thus one can exploit the regularity properties of the heat semigroup to deduce that actually the same regularity of ρ1 is inherited by g epsilon, and the same for ρ0 and f epsilon. So that we end up with the following property. The fact that since ρ0, ρ1 are bounded with bounded support, the same is true for our f epsilon and g epsilon. And since ρt epsilon is given by the product of the heat semigroup applied to such two functions, we deduce that also ρt epsilon has to be smooth in any reasonable, smooth in the case of manifold, or it is a test function in the case of RCD spaces. And so this means that entropic interpolation are not only an alternative way to interpolate between two measures, it's actually an extremely regular way to interpolate between them. So having this in mind, we can now move to the variational representation of the Schrödinger problem. Let me say that all the formulas that we shall see were known to be true in the Euclidean space with Lebesgue measure or with Gaussian measure. So our contribution has been the extension of such results to RCD spaces. So in particular also to the important case of manifolds. This formula was known also before us. I mean, we didn't generalize it, but the other ones, yes. So just for sake of completeness, let me say just that the Schrödinger problem admits a dual formulation. And from a heuristic point of view, if we have a minimizer gamma epsilon of the primal problem and a couple of maximizers for the dual, then such relation must hold. And this tells us that if maximizers exist, then they have to be this form. This motivates the definition that I will give in the next slide. This slide is very important as it summarizes the dynamics of entropic interpolation. So let me recall once more the definition of entropic interpolation. As you can see, it is the product of two functions, the one solving the forward heat equation, the other one the backward heat equation. And motivated by the previous remark, we define the so-called Schrödinger potentials in this way. Notice that they solve a forward and backward Hamilton-Jacobi-Bellman equation, and they are linked to the entropic interpolation by backward and forward Fokker-Planck equation. Furthermore, if we introduce the function theta t epsilon as half the difference of the potentials, we have a third dynamic interpretation, which is given by the continuity equation. So this allows us to rewrite the so-called entropic cost, which, okay, I didn't pay attention, I didn't stress it, it is the minimal value of the Schrödinger problem. Okay, so this entropic cost can be rewritten in this way, and then using such identity and the very definition of theta t epsilon, we can rewrite this identity in three different ways. Then we just rewrite these differences as in this form. And here it is important the remark I said before about the regularity of entropic interpolation and therefore also of the Schrödinger potentials, as we can actually bring the derivative under the integral sign and in a rigorous way. And thus, using the PDE solved by ρ t and theta t, phi t, and psi t, we end up with this dynamical but not yet variational representation of the entropic cost. Of course, these three identities immediately lead us to this inequality, where now the infimum is considered over all solution of the continuity equation, forward Fokker-Planck equation, and backward ones. So in the case of continuity equation, we have the kinetic energy part plus the Fisher information, while in the case of forward and backward Fokker-Planck equation, we just have the kinetic part. Okay, the definition of continuity equation is the one I mentioned at the beginning. While for Fokker-Planck equation is completely analogous, we ask the PDEs to hold in a distributional sense. We ask the integrability of the velocity fields, and we ask the bounded compression assumption. Okay, now we would like the opposite inequality to hold. This can be achieved as follows. In the compact case, one takes any solution of the continuity equation and the best possible choice for the potentials, which are given by theta t epsilon. And then, using again the definition of theta t epsilon, bring the derivative under the integral sign, use the PDEs, the Fokker-Planck and continuity equation. And then, by Cauchy-Schwarz inequality, we have this couple of inequalities, and some cancellation occurs, and so that in the end we have the desired inequality with equality if and only if Vt is equal to the gradient of theta t epsilon, and this condition tells us that nu t is equal to rho t epsilon. In the general case, one has to be more careful, but the argument is essentially the same. So one just has to use cutoff argument, replace phi t epsilon and psi t epsilon by this function to avoid possible lack of integrability, and then pass to the limit as delta goes to 0. So in the end, we have this first result that in Rn was proved by Chen, Giorgio, and Pavon, and in Rn with weighted measure satisfying the CDK infinity condition by Gentile, Leonard, Ripani, and by myself and Nicola Gigli in the case of RCD spaces. And as in the case of Benamou-Brenier formula for optimal transport, we can actually characterize the minimum, not only the velocity but also the interpolation. And we also have two other possible ways to express the entropic cost by means of the Fokker-Planck equation. Then, in the optimal transport case, at this point, we use the fact that continuity equation was in duality with Hamilton-Jacobi. Now we have something analogous in the sense that Fokker-Planck equation is in duality with Hamilton-Jacobi-Bellman. More precisely, if we have a super solution of the backward Hamilton-Jacobi-Bellman equation and a solution of the forward Fokker-Planck equation, then this inequality holds. So that by Benamou-Brenier formula for the Schrödinger problem, if we saturate the right-hand side with the infimum, we have that this becomes the entropic cost, while if we saturate the left-hand one with the supremum, we end up with this inequality. And once more, to prove that actually equality holds, it's sufficient to observe that this function, family of function here, as delta goes to 0, is a maximizing sequence. As a further step, one wants to pass from this Hamilton-Jacobi-Bellman duality to the entropic counterpart of the Hopf-Flachs duality. So one has to replace the Hopf-Flachs semigroup by an entropic counterpart. And this is, okay, this was just to summarize the result. Okay, so the equivalent is given by this definition. Indeed, if u is any function in L2, such that the exponential is in L2 and L infinity, then this gives us a solution of the Hamilton-Jacobi-Bellman equation, so that in the Euclidean case, the result was proved once more by Gentile, Leonard, and Ripani. We extended to the RCD framework, and we have the desired entropic analogous of the Hopf-Flachs duality. So to sum up, we have this very rich picture. So as I said, we have indeed the primal problem, the dynamical one, and of course we have other two ways to represent it by means of Fokker-Planck. We have the Hamilton-Jacobi-Bellman duality and Hopf-Flachs, the analogous of Hopf-Flachs duality and the dual version I stated at the beginning. And looking at this this picture, we can perceive not only the analogy between the two problems, we can also be convinced somehow that as epsilon goes to 0, the entropic, the Schrödinger problem, and so the entropic interpolation converge to Wasserstein distance and Wasserstein geodesic respectively. Indeed, here we expect the Wasserstein, the Fischer information to disappear, and here the Laplacian to be vanishing in the limit. And this is actually the case as proved in a paper by myself and Nicola Gigli. Okay, so in the last part, I will sketch the application of the Benamou-Brenier formula for Schrödinger problem to the study of long-time behavior of entropic interpolations. So, let us now, rescale our Schrödinger problem from the interval 0,1 to the interval 0 epsilon. Okay, in this case, epsilon is no longer a vanishing parameter, can be seen as has to be seen as a diffusion parameter, and we let it tend to infinity. We rescale the entropic interpolation in this way. And from a physical point of view, it's clear what's happening, because our final constraint is getting far and far away. So in the end, it should not affect the behavior of the entropic interpolation. So in the end, we expect that we just have the initial configuration, and since our particles are moving as a Brownian motion particles, we should have only the heat flow. So for epsilon large enough, we expect that on the first half of the interval, our entropic interpolation essentially behaves as a heat flow. In the midpoint is very close to the equilibrium, while on the second half of the interval, it essentially behaves as a backward heat flow. Yes.
What is H? Could you slow down? Sorry, what is H? H prime?
Oh, sorry. This is just H is the Boltzmann-Shannon entropy. So this is it's the gradient in the autocalculus language. So this is nothing but the Fischer information. So yes, in the end, we are just saying that. Okay, so gamma dot, so it's the velocity of the curve, is minus 1/2 the Fischer information, which is an equivalent way to say that this is the heat flow. Okay, so can we prove this conjecture and make it also quantitative? Well, the answer is we're relying on the Benamou-Brenier, on the entropic analogous of the Benamou-Brenier formula. With some computation, we obtain this inequality. And using the entropic Talagrand inequality proved by Giovanni Conforti last year, which allows us to control the entropic cost in terms of the marginal entropies, we are able to get rid of the entropic cost in this right-hand side. And in the end, we obtain that we can estimate the distance between our rescaled entropic interpolation and the heat flow, and such a distance goes to 0 exponentially fast as epsilon go to infinity. And so we made precise the previous conjecture, and we can also get some further information, because using once more the entropic Talagrand inequality, we observe that the entropic cost as epsilon go to infinity converges exponentially fast to the sum of the marginal entropies. Okay, and with this said, I thank you for your attention.
Thank you, Luca.
Quite fast.
Is there any question? Dario.
We saw this morning, for example, if you take a sub-Riemannian structure, K is not bounded, right? But
yeah.
Does your technique work?
We strongly relied on functional inequality that follows from lower bounds on the curvature. So we used Hamilton and Liao. Liao not, but because we worked at fixed. But yes, Hamilton gradient estimate was used, and this requires a lower bound. But maybe one can avoid this by, in particular sub-Riemannian cases, one can use one can do explicit computation. So the same conclusion can hold, but does not follow along the same lines, probably.
Actually, I had another question before, but I forgot. Okay, do you prove can you prove also gamma convergence instead of just convergence of the, or is it equivalent?
You mean as epsilon go to infinity?
Yeah, no.
Well, because as epsilon go to infinity, we are thinking about it. For the moment, we just have the pointwise convergence of entropic cost to the sum of the entropy. The convergence of the rescaled entropic cost as epsilon goes to 0. This was proved by Leonard in general cases. Under the assumption that your reference measure satisfies a large deviation assumption.
Yes. Okay.
This holds on Polish spaces.
Any other question? Okay, thank you again. Well, we have a break with the lecture of Simone Di Marino from the Scuola and the INDAM.
Yes.
And the title is An Entropy Minimization Approach to Second-Order Variational Mean Field Games.
Thank you. So thank you for the invitation. It's always a pleasure to talk here in Pisa. And so I will talk about this problem that is related. I'm fortunate because there was a talk of Pierre and there was a talk of Luca that both introduced some of the things that I will talk about. So I first say the motivation. So the motivation comes from the mean field games. So these are the mean field. This is the mean field games system. So this is describing how a density of people is evolving in time, subject to some control equation that will be this evolution. And so the mean field game system is a forward continuity equation for the density of people, and a backward Hamilton-Jacobi equation for the objective function for phi. And so the mean field game system were introduced by Lazary and Lyons, and a nice structure that they have sometimes, in this case at least, is that they have at least a formal variational formulation. So this is the case where there are quadratic, so-called quadratic mean field games. So here we have the power 2, and here in particular we have linearity here. In this talk I will only talk about this, so the power 2, because so what we use doesn't allow to treat more general case of mean field games. And so was discovered this variational formulation that is very nice, and so we can see that this variational formulation, we have the usual kinetic energy that is so the integral of Vt squared rho t. So this is the kinetic energy of this density of people that go around, and Vt is the velocity at which they are at time t and position x, and plus these two penalization terms. So the last one is f of rho t, rho capital T, that is related to this big phi to the cost at the end. And so this f of rho t is just the integral of big psi in the rho t usually, but we can also modify it a bit and take some nonlinear penalization here, and instead this g of x rho t is what is really guiding the what is really coupling these two equations via this term little g. So big G is the antiderivative of g with respect to the second variable. So g prime is equal to little g, and usually this is something like preventing very much people going through the same place. So usually this is something like rho t squared, in such a way that rho t can't be too much concentrated, and so given this, the people would like to avoid where there is much other people, and this is the complication of the mean-field game system. There is this G that couples the two equations, and so one has to solve in particular for the whole time, because one is forward, the other is backward, and so this is roughly the idea. And so this Eulerian variation formulation has a nice also Lagrangian formulation, which has been approved by Benamou, Carlier, and Sant'Ambrogio. So Luca already spoke about a bit of the link between the Eulerian formulation and the Hamilton-Jacobi, etc., etc. So maybe this is a bit clearer. But I want to speak also the Lagrangian formulation, because this is what will be the aim for the second order. And so I'm concentrating here in order to state the link the link between the Eulerian and the Lagrangian formulation. So the Eulerian formulation is something that is we are looking to the density of time t. So for every x, we see what is the density of our people, and then we take the velocity at time t of this field, this velocity field that the people are following time by time, and we have this kinetic energy in, as I say, in a Eulerian framework. Lagrangian, what does it mean, Lagrangian? Lagrangian, it means that we are following people. Okay, so we have some guy that was at position 0, and we want to follow him. And so basically what we are representing here is this Q. This Q is a probability measure on the space of curves. Okay, it was written here, I believe. Okay, C is it's a probability on C, Q. And so this is a probability on the space of curves, and so it is saying every people which trajectory is following, and then this kinetic energy now is the kinetic energy of a single of a single person. Okay, this is just the integral of omega dot, that is the velocity of the curve squared. In dt. So this is the kinetic energy of this one guy along his path from 0 to t, and then we integrate this kinetic energy in the whole time for every people. So Q is the probability of paths that people are using, basically. And for every path, we know that there will be a kinetic energy that this guy will have throughout the whole path. And what has been proven by Licini is that really these two quantities, so the Eulerian kinetic energy and the Lagrangian kinetic energy, are really the same, having fixed only what is the density rho t time by time. So I'm fixing just the density rho t by time. I know that the people will be here and there, etc., etc. And then what I want to do here is minimize among the velocities, the velocity fields that allow this density to move in this way that I fixed, and I minimize the kinetic energy among all these velocities, and I can do the same with the Lagrangian approach. So I minimize among all these probability measurement curves this kinetic energy, given that at every time I should have that at time t, when I superpose all these paths with probability q, I obtain again rho t, that it was the fixed density that I choose. And these two quantities are also in particular equal to the integral of the velocity squared in the Wasserstein sense. So rho t can be seen as a curve, as absolutely continuous curve from 0t to the space of probability densities in Rd, and I can consider the velocity in this space, and the kinetic energy in this sense is equal to these two guys. Now I won't need this first characterization, but it is important to know that these two are equal. And this is a way to say that the Eulerian kinetic energy is equal to the Lagrangian kinetic energy. So there is this duality that is all over optimal transport usually. And so here now we can see that these two are equivalent, because now you imagine you fix rho t for every t, and then you minimize only this guy here, and then this guy here will be equal to the minimization of this guy here. That is precisely what I wrote in the next slide. So the integral of the kinetic energy of the single people integrated with respect to q. And these two terms are equal just by definition of ET, q, etc., etc. Okay, this was the Lagrangian formulation, the Eulerian formulation, and the mean field game system in the first order case. And what I want to talk about is the second order mean field games. What do we mean by second order mean field games? Well, we just add some viscosity, the viscosity on the density and also on the phi, and this amounts to add some from Brownian motion to these people. So these people wants to follow some optimal path, but there is also some Brownian motion that is adding to it. This can be made also rigorous via stochastic differential equations, but I won't talk about it. Instead, I want to talk about the Eulerian variational formulation and what we proved, the Lagrangian variational formulation for this problem. And so we see that the action we are minimizing for this kind of problem is the same as before, is really the same. So in the kinetic energy, this time it's not a kinetic energy, I won't call it kinetic energy anymore. So it's 1/2 Vt squared rho t plus Gx rho t plus F rho capital T. So it's really the same, but now the constraint, before it was just the continuity equation. Here instead we have the Fokker-Planck equation. Okay, and this you have to think of as in the talk of Luca. In the talk of Luca, the idea was basically you can look at the Schrödinger problem, but also the optimal transport problem, as a mean field game system with the G equal to 0. So they are not coupled here, but they are coupled instead here. But we don't have anymore the final condition on phi. But if you want, it's just so G equals to 0, and then F equals to 0 if rho capital T is equal to some measure nu, and plus infinity otherwise. So we are constraining rho capital T to be some measure. And then this is really the formulation that Luca gave, the dynamical formulation that Luca gave for the Schrödinger problem. In one of the formulations, of course. So where we impose a forward Fokker-Planck equation, and the energy is 1/2 Vt squared rho t, and that's it. Now here we are adding also this coupling term in order to recover the main field game system, and we have a general penalization for the arrival density. Okay, and what is the Lagrangian formulation? Well, the Lagrangian formulation is very similar to the first one, of course. And so we have again the term with the capital G and F that are really the same. And then the term with the kinetic energy will be substituted by the entropy of Q with respect to R epsilon, where R epsilon is the Wiener measure of variance epsilon. So is the law of the Brownian motion with variance epsilon. Okay, so this is what we want to prove, really. And why do we like this kind of formulation? We like this kind of formulation because, as we will see, maybe this is related to the entropic regularization of optimal transport. That is a fast way to approximate the optimal transport in general. That is so in solving the Schrödinger problem, if you will, with epsilon very small, we are almost solving the optimal transport, and there are very fast numerical methods to solve this. And in particular, when epsilon is big, is much easier. So the idea is that for epsilon big, not very small, this will be very easy to compute numerically. Of course, there is the relation with the entropic optimal transport, otherwise say the Schrödinger problem, and then the other fact is that again, as epsilon is going to 0, this Lagrangian second order converges naturally to the Lagrangian first order, because it is known that the entropy of Q with respect to R epsilon is gamma converging to the kinetic energy. Okay, and also in a way this is a way to treat the mean field game system of the first order, just adding leader epsilon and then solving with this entropic optimal transport numerics. Okay, now I will talk about the Schrödinger problem, and I will add this. Luca already explained several equivalent formulation. I have to add another one that is the Lagrangian formulation that is equivalent to the others that Luca already said. Unfortunately, my notation is dynamical for Lagrangian. Instead, his was dynamical for Eulerian. I hope that it doesn't bring too much noise to the problem. So okay. This is the one of the formulation that Luca gave. That is so we are minimizing the entropy of gamma with respect to the Schrödinger, the Wiener measure. Sorry, this is not the Wiener measure. This is the heat kernel, if you want, the heat kernel at time 1 with the diffusion epsilon. So the entropy of gamma with respect to this measure, where we have these two constraints. So the two marginals have to be rho 0 and rho 1. This is the static formulation for us. The dynamical formulation, that is the Lagrangian formulation, again is very similar. Instead of minimizing among couplings, we are minimizing among probabilities on curves. And now this time we do the entropic we do the entropy of this Q with respect to the Wiener measure, that is a measure on paths. Okay, and so Q is a measure on paths, and we have again at the starting time, at the final time, when we superpose these curves, we should obtain again rho 0 and rho 1. So these are the two formulations, and Fulmer proved that in fact these two values are equal, and in fact the minimizer Q star for the second one and the minimizer gamma star for the first one are related, and gamma star is the marginal E0 E1 of Q star, and Q star is equal to we can disintegrate Q star with respect to gamma star, and what this integration says is that for every x and y, so we are conditioning. This is, if you want, the conditioning of Q star with respect to a starting point and a final point, and we are saying that for the optimal one we should have always a Brownian bridge. The conditional probability will be always the Brownian bridge, and I want briefly to prove this. It's very easy. So let us consider Q star that is an optimizer for the Lagrangian one. So we can disintegrate with respect to its marginals E0 E1, and so QXY will be something will be a probability measure on the space of curves, concentrating of curves that starts at x and ends at y. And similarly, we can do the same for our epsilon, and we know already that this is the Brownian bridge dx dy. Then, when we do the entropy is very nice because it behaves in a very nice way with respect to conditioning. And so, what it happens is that okay, I read it here. Is that HQ star with respect to R epsilon is equal to the entropy of gamma, that is the marginal E0 E1 of Q star with respect to the marginal E0 E1 of R epsilon. We know that this is greater or equal than this. This is very easy. But then we know what is the remainder, and the remainder is the entropy of the entropy of the conditioned probabilities of Q star and of R, integrated with respect to the gamma. So if you want, when you are projecting these two measures with this function here, basically we have we will have the entropy of the push forward probabilities plus, and then you have the disintegration, and this decouples in a very nice way, and this is really an inequality. And since the entropy is always greater or equal than 0, we have that this is greater or equal than this entropy here, and this already proves an inequality between these two. And in order to get the other inequality, it is sufficient to note that if we fix now gamma, it is sufficient to take QXY equal to RXY epsilon for every XY, and then we construct Q star in this way. So now we look at the reverse. So we fix gamma and we construct Q star, and we get equality here. Okay. So this is the idea of Fulmer, and okay, and what Luca said is that this minimization problem. So we are minimizing 1/2 VT squared rho t subject to the forward Fourier-Planck equation. Then we have that this FP stands for Fourier-Planck, of course. Fourier-Planck between rho 0 and rho 1 is equal to the Schrödinger problem plus the entropy of the initial condition with respect to the initial condition of the the Wiener measure that is the Lebesgue measure, so it's just the entropy rho log rho. And this is, of course, we say that the static and the dynamical are equal, so we have equality. And okay, this is what Mikami already proved in the 90s, and then Leonard in full generality on Euclidean spaces, and then it has been expanded, as said by Luca and Nicola, to every to every metric measure space with some suitable condition. Okay, so now in this setting we can go from the Eulerian formulation to the Lagrangian formulation, because this is the Eulerian formulation and this was the Lagrangian formulation. So the Eulerian and the Lagrangian are equal also in this case. And now, okay, this is just the comparison with the Monge-Kantorovich, the classical Monge-Kantorovich. And so this is the static formulation. Again, this is the Lagrangian formulation. This is the Lagrangian formulation of the level of optimal transport. And then these two are equal. And what Leonard proved, and then by Carlier and others, is that as epsilon is going to 0, how I call them, these S stat and S din, as epsilon going to 0, they converge, they gamma converge to this optimal transport problem. This is what allows us to say, okay, let's take epsilon smaller, we solve numerically, and then we can say that they are close. And this is, and the Eulerian formulation for the optimal transpose is not other than the classical Benhamou-Brenier formula. And okay, this is what is happening at the level of Lagrangian, at the level of Lagrangian picture. I hope that this clarify a bit what I am saying. So in this case, so we have the red points are rho 0. Rho 0 is the sum of some Diracs, and the Diracs are the red points, and the blue points are rho 1. Okay, so we have sum of Diracs. Then this is the Lagrangian picture for epsilon equals to 0. So the optimal transport. So what I'm saying is that now time is going from 0 to 1, from red to blue. So this is the position of the various guys at time 0, 0.1, etc., etc. And they are moving on straight lines. This is well known in optimal transport. You are moving on straight lines when you're doing the geodesic. Now, what happens if epsilon is a bit larger? Now, two phenomena appears. The first phenomenon is that you don't go anymore on straight line, but you do this. What represented here is the Brownian bridge between these two guys. But the other phenomenon that is appearing is that we aren't anymore deterministic. So this is not only coupled with this one, but also a bit with this one. And this, as epsilon is larger, we can see that the bridge broadens and it becomes fuzzier and fuzzier. And this is, if you will, this is related to what Luca said at the end. So if epsilon is very big, of course you have a Brownian bridge from here to here with epsilon very big. It's just spread out on the whole space, and then it comes back here. So when you superpose, of course, at epsilon, at time t equals 1/2, you expect to cover everything in a uniform way. Okay, so let's try to arrive to the Lagrangian formulation in the second order. Okay. So the idea is that now we have the Lagrangian equals to the Eulerian in the Schrödinger problem. Now we want to use it to prove that this is true also at the continuous level. Now the idea is now to discretize time. Okay, we discretize time and we fix some points rho 0, rho 1, rho n, and we fix these n+1 time steps, and we introduce this new kind of problem. This is the Lagrangian formulation for this problem here. What I'm saying here, I'm minimizing the entropy of this probability on curves with respect to the Wiener measure again. But now here we are not fixing anymore only the starting position and the end position, but we are imposing that also in the middle we have some fixed row, we have some fixed density. Okay, so we are fixing the density at time 0, 1 over t over n, 2t over n, etc., etc. Okay, and now this problem, okay, we will see in a moment that behaves in a very nice way. It actually decouples it splits in several little pieces. So again, as proven by Föller, it is easy to see that this Lagrangian problem is equal to some static problem where we are minimizing only the entropy with respect to the entropy of some probability measure on the x to the n+1 space with respect to this multi-time hit kernel, if you want to, and here we are fixing again some marginals. This is, if you want, this is an entropic regularization of a multi-marginal optimal transport problem, and okay, and the idea is again the same. We are taking this function that is e0 to up to en, and we are doing conditional probability with respect to the to fixing all these points, and again we run basically exactly the same argument as before, and this will prove that in fact this static problem is equivalent to the Lagrangian problem. And again, if you want we want to recover the Lagrangian minimizer, knowing the static minimizer, it is sufficient to multiply it by this multi-Lagrangian bridge. Now this is a probability measure on curves that is concentrated on curves that are at point x1 at time 1, at point x2 at time 2, etc., etc. Okay, so it will be something like this. And the very important thing about that let us finish the proof, and it is important in this lemma, is that this multi-Brownian bridge is not other than the product of Brownian bridges, and this is because the Wiener measure has a Markov property, so it doesn't matter what have you done up to here, it will be independent, and this allows us to say that this is a product of measures. And thanks to this product structure, using basically the fact that if we are minimizing an entropy with respect to some product measure, fixing the marginals, we are just the optimal choice will be a product measure. This I will write in order to be clear. So what's behind the next lemma is this fact. So if I have E0 sharp gamma equal to rho 0, and E1 sharp gamma is equal to rho 1, and then I want to minimize the entropy of gamma with respect to some product measure. That doesn't matter which are these mu0 and mu1. Then, okay, I put directly argmin in this category. Then I will have that gamma is equal to rho 0 times rho 1. So this is very easy to prove, and using this, and again the conditional probability trick of the entropy, we can prove that this static problem. So here we have this entropy of the probability on n states with respect to the multi-time hit kernel. It will split in static problems of 2 consecutive times. Okay, so this is equal to the sum of these minus these entropies. Okay, and of course this is true also for the Lagrangian problem, because we have the equality at the level of 2 marginals and then at the level of n marginals, so we can pass to the limit. And now the idea is this one. So now we take this Fokker plan n with respect to rho 0 rho n, so we consider the minimization of this 1/2 vt squared rho t with respect to the so fixing constrained to having a Fokker-Planck equation satisfied, and now we're fixing at some time ti the measure rho I. Now this of course is equal to the sum of the Fokker-Planck between 2 consecutive times. This is of course because you can split these according to time and then minimize every little piece. This is clearly additive. And now, thanks to the first proposition, so the proposition we said about the Schrödinger problem. The Schrödinger problem, we showed that the Eulerian is equal to the Lagrangian minus this term, and so we have exactly the term here that is precisely what we proved in the slide before, be equal to the static problem of the multi-marginal type, where we fix the n at n times steps, and it is again equal to the Lagrangian. Yes. So again, here we proved that in this multi-marginal problem, the Eulerian problem is equal to the Lagrangian problem. Now, to end the proof, now the idea is that we do a gamma convergence result of this functional here, of this functional here. So we take the Fokker-Planck, so we discretize our objecting function that we wanted to minimize, and so we have this is again this energy here, plus then we have a discretized version of the integral on time of g over I, and this is always as it is the final penalization term. And then what we proved is that when n is going to infinity, so we will making more and more time steps, then this functional is gamma converging to the real functional that we are interested in, that is this one. And in particular, what we can prove is that the minimizer of these are converging to the minimizer of these, thanks to the gamma convergence. But now it's easy to see that the Lagrangian is converging. The Lagrangian with n fixed marginal is gamma converging also, and so since we have the equality at the level of n and they are both gamma converging, also the final problems will be equal thanks to the gamma convergence. And so what we really in fact can able to prove is that the Lagrangian problem is equal to the Eulerian one. Okay. How much time do I have? 10 minutes. Okay. Now I don't want to bother too much with the numerical scheme, also because I'm not very an expert. I borrowed some of the slide from one of the co-authors, but the idea. Now I want to say, okay. What I want to stress is just the two marginal case. So as Luca was saying, solving the Schrödinger problem amounts to find a representation like this. So gamma, that is our coupling between two, now this is two marginals with fixed marginals. This is not anymore mean field games. We will see later what we have to tweak. So we have to find some gamma that has this form here. So we have R epsilon, that is the heat kernel, times some function of only the first variable, so phi x. This is what was called fx, I believe, and this is gy. Now in this case, x becomes I and y becomes j because it's already discretized. If we find gamma such of this form, such that the marginals are equal to rho I and rho j, we are done. Okay. So the very easy idea is, okay, we iterate. We want to find the fixed point of this kind, and so this gives us directly the iteration. So the iteration will be like this, and this is proven to converge very easily. And the beauty of this is that it's very easy and it's also very fast because okay, here we have some problem of dimensionality. We have to store here some maybe very huge matrix, but it has the good advantage that this matrix has a very nice form because it's basically we are applying the heat kernel to something. So by Fourier analysis, it is very easily done. In fact, this is so we are really taking advantage of the form here of the nucleus here. At least in the Euclidean setting, if one has a domain or something like that, is much more complicated. This works very well on the torus, or if you want to on the whole Euclidean space. And so the theorem says that An and Bn, they converge to A star and B star that are solution of these. And okay, now the idea is that this is. Of course, the first term is very similar to this term. Is basically the same, but we have more marginals, and then we have this kind of penalization term. But then one tries to see what is the what will be the solution of this, and the idea is that when looking at the Euler-Lagrange equation of this, we have again that the solution will be of this form, but now the constraints are not anymore as simple as before. We had just to sum up on the various indexes, and then we have hope to find the right density, but it's something a bit more complicated, where here we have again the sum of all that we have to do. This is the hard part, and this is something, okay, this we are minimizing with just one variable. We have the entropy, and then we have this guy here, and this minimization is not very difficult to do. It depends on the shape of Gn, but for example, when Gn is a usual constraint that maybe we can have in mean field games, that is we want to have rho less or equal than 1, then this becomes very easy. This becomes if I'm not mistaken, is really, so it is like the numerical scheme for the standard one, but plus we just say, okay, we take the minimum between that number and 1, so it's very easy and it's explicit. And so in order to deal with so this was to deal for yes, this is both for multi-marginal and the adding of Gn. Okay. Yeah, sorry, I was a bit sloppy here. Now we'll take some time to let you see what are the numerical results. So this is hard congestion. That is we have the constraint rho less or equal than 1 with some obstacle, because the obstacle you can look it at. Okay, we can't see anything here, but okay, here maybe it's more clear. So there is an obstacle here, and this I would say that is so we are starting from a density here, we have to end to another density here, and this is the path that is following, knowing that here we have some obstacle that we cannot trespass. And also the obstacle are very easy to say, because you say, okay, rho must be equal to 0 in that zone here, and otherwise you have to be less or equal than 1. And when we have this bound of this kind, it's very easy to do it numerically. And this is another generalization with the moving obstacles. So we have this ball here, red ball, that is moving, and we are saying that, okay, we have to go from the bar to, in this case, we have an objective function, so we have to minimize some objective, and instead here we have, okay, multi-obstacles that are moving, and we want to go to from the horizontal bar to the vertical bar. Okay, and this is it. Thank you for the attention.
Thank you, Simone. Any question? So, thanks again.
Thank you.
Sì, sì, troppo. Ok. Così in tasca.
Allora è meglio.
Sulla camicia? Così?
Sì, sì. Ok, puoi giocare qui?
Aspetta, cominciamo subito. Sì.
Let's go to the last talk of this afternoon by Dario Trevisan from University of Pisa. And the title is Gaussian Optimizers for Entropic Inequalities in Quantum Information.
Thank you, Giuseppe. Thanks to the organizers. I'm not part of the organizers team, although I was somehow involved into some organizing works. Anyway, to my joy. Oh, anyway, it was nice because at least I know the title of all your talks. So about mine, this is a joint work with two physicists, Vittorio Giovannetti, who is a professor at Scuola Normale, and Giacomo De Palma, who used to be so he's a former PhD student of Giovannetti and now moved to Copenhagen at the Kumas Institute. I also added the name of Luigi Ambrosio because this talk is based on a review paper where we tried to sum up some of the open questions and conjecture some results about this topic, which I would say is very hot in quantum information theory. And it would be nice to get some insights from a community which is different. And in fact, I will mention there is no real breakthrough by optimal transport, even if some people in the audience may argue it is not the case.
in this framework. At least the conjectures I'm mentioning, some of them may require some ideas from optimal transport. So, of course, the outline is very ambitious, but I don't know if it's too long. Please stop me. Of course, we need to introduce some quantum vocabulary, some notions, and I think the best way to learn these things, if you don't know about it, is by comparison with what is the commutative measure theory, in particular what are Gaussians in the classical setting, and then compare them with the bosonic quantum setting. Then I will try to do an overview of the inequalities and what are the main conjectures from our side, and some ideas of the proofs of the partial cases we were able to do, and some contribution from other authors. But really, okay, let's see where we can go with this. So of course, we have to compare notions that we know with something which possibly you don't know. Maybe you already studied quantum mechanics, but I'm not supposing this. So the idea is to replace classical objects with the quantum counterparts. So the first idea is to change points in a set, which should be a measurable space if you do measure theory. Change points with vectors in a Hilbert space, vectors that we denote with the physicist notation, just for the sake of using the same notation in the paper. Of course, given a vector which should correspond to a point, you can, being a vector in a Hilbert space, you can also use the dual vector, which will denote, duality will be denoted with this dagger, also for operators. So the idea is to replace points with vectors and functions with, okay, you can replace it with operators, with the linear operators, possibly not defined on the whole space, and requiring other regularity properties. So this is really the quantum framework, but if you want to do non-commutative measure theory, you have to add some measure, and possibly compute norms and do probability as well, right? So instead of a reference measure, on our Hilbert space, which should be the measurable space, we will deal with the trace, okay? So why the trace? Because it has the nice properties you would expect, in the sense that if you have a function, the integral should be the trace. Of course, in infinite dimensional spaces, you have to be careful about it. But in particular, the LP norm of a function, which should be what the integral of the p power of the norm, the pointwise define the norm. Of course, instead of looking at points, you just do the trace of this sort of x squared. You symmetrize, because x in general could be also non-symmetric, right? So you do the trace of x dagger x to the power p over 2. This is, of course, say that you are in finite dimension cases. These are just matrices, and then everything is well defined. Otherwise, you have to be careful and use, for example, spectral theory to define the power p. Anyway, in this initial slides, you can think really of a finite dimensional Hilbert space, and all these notions are perfectly defined in any case. So now, given this framework, okay, we have what should be the triple A sigma algebra, which here does not appear, and the measure, a reference measure. So we can start to do some measure theory. A lot of natural questions have been solved in general. Something is true, something not so true in the quantum framework. But for example, what is the counterpart of a probability measure or a probability density? Here I'm a bit sloppy about this. Well, there is the crucial notion of quantum state, okay? Because while a point is just the operator, is just a vector, sorry, a quantum state is really what you think about of a probability measure. So it's just a symmetric operator. Actually, we take it of trace class. Okay, so it is compact in general and non-negative, of course. So, and this is really what you think of a probability measure, right? It's non-negative, sum equal to 1. Now, given the notion of state, which will play a key role, one can deal, for example, of expectation of a function with respect to the law of a random variable, mu, right, f of x. Well, this becomes really the trace of x times rho, where x must be symmetric, actually is self-adjoint to talk about observable. These are special operators. Anyway, this will not use, just to make an example of what is quantum probability and expectations. A crucial notion instead is what in classical commutative measure theory is a delta measure. I was asked, for example, not today, but 2 lectures ago by my students, because I was using delta without defining. What is a delta measure? In measure theory, it's a very simple measure, but you can think also of it as an extremizers for in the convex set of measures, right? So in this case, if you think about this, the corresponding notion in the quantum setting is what is called a pure state, a state which cannot be decomposed as a convex combination of other, or non-trivial convex combination of other states, and it must be of this form. Essentially, it's a rank 1 projector, right? It's symmetric and trace is equal to 1 if psi is normalized. Otherwise, if it is not norm 1 is not a state. Okay, so keep in mind this fact that delta measures corresponds to pure states, because one of the problems or exciting things about quantum theory is that compared to the commutative case, there's a plenty more of pure states, okay, which does not correspond, okay, to our intuition of delta measures. Okay, now if you have instead a probability density, well, I'm just saying just to compare two notions, you can think of probability densities as functions times a measure. Well, it's not really a true counterpart here, but you can always use the spectral theorem to decompose a state and obtaining some discrete probability densities, probabilities pk, so these are really numbers between 0 and 1 which sum up to 1, the series, times pure states, which are just projectors on this still psi k have norm 1, so these are pure states. Okay, so it's somehow the analog of this decomposition. It's really an analog, I'm not saying it's an equivalent. And then just to add something important in our talk is what the physicists call entropy. So this is Shannon differential entropy, and notice the minus signs, okay? This can be a bit confusing, but physicists want the entropy to increase along the heat semigroup, for example, so they just, well, not only physicists, I think historically was really defined with a minus, okay? I don't know which was the community who decided to switch to plus. Anyway, this can be a bit confusing. I will stick to this notion, okay? And if you have troubles with that, we'll clarify. Anyway, von Neumann put forward this definition before Shannon did, and actually it was inspired by Boltzmann's notion of entropy. And of course, again, this trace of this function of the state, rho log rho, is defined by spectral calculus, and this is just minus the Shannon discrete entropy, okay? Sorry, the minus is included in the definition. So it's minus a sum of pk log pk. But of course, it has different properties. I'll try to mention some different properties than the classical entropy. So one huge difference between classical and quantum settings, if you really want to compare this, when you move to product spaces. Okay, in general, of course, if you start with a space, it could be already a product space. But when you try to define this operation, you end up with things which are very weird or strange. But you can work with them as well. So the classical case, you can start with a product, the classical product space. You take the product of the points and product sigma algebra, and of course you can define product measures, for example. And in the quantum case, okay, you have a notion of Hilbert product, the tensor product of the two Hilbert spaces. And then, of course, you can define product states, which are just take an operator, and then you do the tensor product of the other operator. In terms of matrices, this is a well-known operation between matrices. Now okay, I'm forgetting the name. Anyway, this is just the operator which acts on states which are product states by acting component-wise, if you want. Now, what is the problem? Is that if you think about pure space, pure states, so a state is pure in the classical framework. I told you if it is a delta on some point, but a delta at the point xy is just the tensor product of delta x times delta y, right? So pure states are really product states. There is no difference. Instead, in the quantum case, I told you any state which is pure is just take a vector and do this projector on the unit vector, of course. Now the problem is some of them may be product, in the sense you take a vector which is the tensor product of two, others maybe not, and this is what physicists call entangled states, okay? And this is really the idea of there's so many pure states then you can think about it. I mean, there are all the entangled states, and they have strange properties. For example, in the classical case, given a measure, not only a product measure, but any measure on the product, you can do the push forward on the factors, and you discuss what is the marginal, right? So I write in this way because to compare with the quantum case. If you have a measure mu on the product space, you can really somehow integrate the second component and end up with a marginal on the first factor. And there is the analog. The analog is the so-called partial trace. If you have a state on the product space, you can do what is called the partial trace. So you do the somehow you fix an orthonormal basis on the other state, and then you sum up only on the factor b. Okay, and this gives you a state. You can prove that states map to states on A. So, okay, we can discuss what are the marginals. You can think maybe we can do optimal transport. Yes, but there is a problem with the other operation, which is rather natural, which is the disintegration. So if you have a measure on the product space, in general, you can always disintegrate it given the marginal, and then what, okay, you can call it as a generalized transport, since we are in the optimal transport conference, right? If this is a probability measure, you get a probability, and then this kernel, which tells you how the points at X split and go to different points in the second factor, right? This is a generalized transport. Well, the problem is that there is no analog in general for this type of disintegration. Of course, there can be states which can be represented in a similar way, but in general, this cannot be the case, because essentially of entangled states. Because if you know that this is pure, but not product, how can this be? I mean, the problem is that already if you start with an entangled state, the marginal can be not pure as well. If you do just the trace of one of the factors, you start to essentially think it's like starting with a delta, and then you look at only one marginal, and it is not anymore a delta. It's like a really diffuse probability. And so you can even not hope to really find a disintegration like this, I mean, in general. And this is one of the first problems, which has a lot of other reflections in the inequalities. Okay, so it's a long lecture on this. So Markov kernels, as I told you, are a basic object. You can define them in many ways. For example, you can think of them as operators on measures, which are linear, positive, and preserve mass. And essentially, they have an integral representation as this, right? When you want to push forward a measure with a kernel, you end up with this representation. There is the analog in the quantum case, although there is no such representation. So these are called quantum channels, and they really correspond to kernels. Essentially, these are operators on L1 spaces, linear, positive, forget about completely, which is not important for us. They preserve mass, they preserve the trace on states, so they map states into states. And there is an analog of this kernel representation, which is called the Stein spring representation. And this is the common way you introduce channels, explicit channels. I will show you the Gaussian case. So what does it mean? It means that if you have a state, or in general an operator, you can transform it and obtain another state, or more generally operators. And then by this way, you do, essentially you enlarge your target space. So instead of just doing B, you take the tensor product with an additional auxiliary space, and then you introduce a unitary operator between A to this product, which somehow you could think about possibly a kernel. It's not really a kernel. And then you trace out this auxiliary operator, which somehow it has to disappear. So at the end, you end up with an operator which maps states on A to states on B. So really this Stein spring representation is very important, and it has also a commutative analog, just to mention, which is different from the kernel representation. So it's really an analogy, it's not the same. For example, this Stein spring representation gives you a notion of complementary channel, which is like this. You enlarge your system, and instead of tracing out the auxiliary system, the ancilla system, they call it, you trace out the B, and you end up with a different channel. And this has no analog in this representation here. Other things which have analogs are the dual of a Markov kernel, so which maps functions into functions, and as well here you get a notion of dual just by duality with the natural integration, which is the trace. Okay, so these are just the Markov kernels. So a natural question which we try to study is the notion of the norms of these operators, and more generally also the limit as p and q goes to 1, which gives you some entropy bounds for these operators. So there is the definition of norm of a Markov kernel. Okay, this could be plus infinity, but formally is this one, as you expect, and is the same in the quantum channel. The point I want to stress is that in general, due to this entanglement, when you move to product spaces, the product of the norm of two operators is not the product of the norms. And this causes a lot of troubles, you will see. Okay, once more. Okay, now this was just the abstract case. I want to move to the Gaussian case. I mean, we want to speak about Gaussians. So you cannot speak of Gaussians on a general abstract measure space. So you have to move to, for example, a Euclidean setting, finite dimensional, for example. So the easiest analog of what is the Gaussian in the non-commutative quantum case, which is the so-called bosonic setting, is that of R2, not just R. So we can identify R2 with the complex numbers, and the counterpart in the bosonic case is this infinite dimensional Hilbert space of L2 over R. So you have just the line, but remember that points are not the points on the line, but are the vectors here, so just square integrable functions. And this is just the wave formulation of wave representation of Schrödinger, right? So, but if we really want to push forward the analogy, so you can say that the coordinates of these points, so if you take a point QP in R2, should correspond somehow, the coordinates should be given by these two operators which are non-commutative. So if you take Q, which is multiplication by X, and P, which is minus ID derivative of X, these are just the position operator and the momentum operation, they don't commute. And for computational reasons, it's better to move to somehow a complex notation. You do Q plus IP, you normalize. Okay, this is not relevant in the Euclidean case, but here it's better. You can really introduce a single complex operator, which is what you call annihilation operator, and then the dual, which is the so-called creation operator. Okay, and so the counterpart of this complex number is this operator. Its dual is also the counterpart of the complex conjugate of Z, and the square of the norm, the Euclidean norm, is what is called the number of operator in the bosonic case. And so what is the second moment of a probability measure is what physicists call energy. And energy is just the second moment of a measure, or just the trace of n, the number, times rho, a state. Now let me mention that this is also in the infinite dimensional commutative Gaussian setting is very studied because of this Fock basis. If you look for the eigenvectors of n, you end up with the Hermite polynomials, essentially. The first, the zero vector is just the one in the kernel of A, which is just the standard Gaussian, depends on what you call standard, and then you can obtain a basis of eigenvectors given by this operation here, by acting with the creation operator. Okay, now this is maybe a bit, I don't know, complicated at the first time, but I really have to think of this analogy. And so if you want to define a Gaussian in this setting, you can say, okay, a Gaussian density is some density which is proportional to a exponential of a second order polynomial. You can write down here a covariance matrix, inverse covariance, and then you end up with this expression in the classical setting. In the Gaussian setting, in the quantum setting, it's a similar definition, but you have to be careful about what is this matrix here. In general, this is not the covariance. I will show you. And in general, if you take any, also here, if you take any sigma, it's not a probability measure, so you have to satisfy some conditions. For example, a very simple example of Gaussian density is the one where this covariance is the multiple of the identity, and you get what in the quantum case is called a thermal state of some energy E, which is just a state which is proportional of the exponential of the number operator n, which really plays the role of the norm of z squared. Now, you can compute things on this. For example, here you know that the energy is proportional to the inverse of this beta. And here you can do the same computations. The point is that you know the basis, you know the Fock basis, so you do all these, you play out with these definitions. You end up with a different thing. You end up with that beta, this parameter, is proportional, actually is equal to log of 1 plus the inverse of the energy. So for large values of the energy, this corresponds in the sense that you can forget about the log, right? You do a Taylor expansion. And this is not uncommon. Essentially, what happens for large values of energy, you end up somehow in a classical limit. But in general, it's not the case. So also the entropy should be proportional to log of E. Now, I'm not sure about the sign. And this is the same. This is not the same in the quantum case, but if you do the limit for large values of the energy, you end up in this asymptotically you are the same. Okay, so we have this notion of Gaussians, and let me move to the kernels, and this is the last slide of definitions, and then we just show you the conjectures. The point is that there's plenty of Gaussian kernels in Rn. By Gaussian, I mean a kernel which may be a Gaussian, but maybe also degenerate. Essentially, I think of a delta as a degenerate Gaussian. This is rather natural. So, for example, if you want the translation operator, which maps z to z plus a constant, z0, can be thought as a Gaussian kernel, essentially, because it's really a Gaussian with zero covariance and mean z0. So there is an analog of this. It is called a displacement operator, and it's an operator which acts on this complex variable non-commutative by translating it. Of course, you have to make a conjugation here. You translate the original variable of z0 times the identity. So there is an analog. For example, having this notion of translation, you can do what is called the heat. Of course, in Rn is the heat kernel, which is just a composition, it's a convolution between the original measure and the Gaussian. And you can obtain something analog by looking at the quantum heat kernel, quantum heat semigroup. It's also a semigroup in T. You just do a translation of square root of T z, where z is a usual standard Gaussian. Now forget about the factors here, is not, it just shows a different normalization. But actually, we're not interested in the quantum heat operator, but in the analog of the convolution. Also, convolution can be thought as a degenerate Gaussian. In general, convolution is just the law of the sum of two independent variables. You denote it in this way. Now, there is the analog. In general, you cannot just simply do the sum of these densities, but you have to look for transformations which preserve the commutators. And this structure is preserved by the so-called beam splitter operation, which has also a physical meaning. In the sense, it means if these are density of particles, the beam splitter is really physically the operation of, for example, if these are photons, you can let them through a mirror which is partially reflecting and partially absorbing, and this parameter is reflected by this lambda. And so you see, it has a typical structure, as I told you. This is a Stein spring representation. You take the two densities, you do the tensor product because they are independent, and then you do this. You introduce this u, which is like a rotation of the modes, but it's a nice operation, and then you trace out one of the two. So it's not really a convolution, it's more like what you call an Orsten-Uhlenbeck, if you remember the classical Merler formula for the Orsten-Uhlenbeck, it's really similar like this. But in the Orsten-Uhlenbeck case, you add a Gaussian. You do this rotation by adding also an independent Gaussian. And this is also something that people in quantum information call a quantum attenuator. Okay, so you take a state, you add a Gaussian, and then you rotate and you trace out. Finally, the last operation is when you actually don't add anything, you just obtain what is called a dilation. You just dilate with a factor square root of lambda. Okay. Well, this also has a name. Unfortunately, all these names are very fancy, but it's very simple. It's just when you take, you add the so-called, the first eigenvector of the Fock basis, you obtain what is called the quantum limited attenuator, which is just a counterpart of a dilation. Okay, now I have at least 5 minutes to show you the conjectures. Okay, okay, and then just give you the statements. Don't want to kill you with this. The problem is really, it seems natural if you look at just the analogies. The problem is when the difference appears, so you cannot prove what you expect. So I told you there are all these Gaussian channels, which corresponds to Gaussian kernels, and there's a very famous theorem by Lieb, proved in the 90s, which states essentially that quantum Gaussian channels, no, sorry, forget about the quantum, Gaussian channels have Gaussian maximizers. So if you want to compute the norm of essentially any classical Gaussian kernel, but even for example, even multilinear, even if you do in the convolutions, right? You just have to look at Gaussian inputs. You just have to test it with Gaussian functions. So the analog of this is what we will call the quantum Gaussian channels have Gaussian maximizers, and this is a conjecture which we call partially solved, essentially, because in some special cases this is known, but not in the general case. And this implies, as usual, I show you, if you move from norms to entropy, you obtain what is called the constrained minimum output entropy of quantum Gaussian channels. This means that instead of looking at the PQ norm, you just look at the entropy produced when you put a constraint on the input of the entropy. These have a very important, more than this, they are very important in quantum information, also for practical purposes, like the so-called capacity of communication channels and so on. And this is also partially proved, essentially, in this case. Now, there is a red conjecture. What is this red conjecture? This is also, essentially, it's a bit partially proved because it implies this yellow, so something must have been proved. The problem is that it deserves a name because it's just the analog of the Young inequality for convolutions, but not the classical Young inequality as you maybe teach at, I don't know, analysis 2 maybe, but the sharp one, the one with optimal constants, okay? And this is a result which is related to the conjecture, the theorem by Lieb, but we put it in red because it's much harder, we believe. And this implies, as usual, when you move to entropies, to a nice inequality which is popular in this community of physicists, which is called the so-called entropy photon number inequality. In turn, this implies other results, but it's largely unproved, I would say. There is a nice result which instead is proved, is the so-called quantum entropy power inequality. Now I give you a hint about this, and this red one, okay? And then we stop. So, as I told you, Lieb proved that for essentially any Gaussian, if you look at real Gaussian kernels, this is for any Gaussian kernel. If you look to complex kernels, there are some limitations. So if you take a usual kernel, but you require it to be Gaussian, so it means the log, so it's exponential of a quadratic polynomial, then if you want to understand the norms of the norm from P to Q, you just, which is in general defined in this way, you have just to look at Gaussian functions f. So this means that you test with rho, which is a generic Gaussian, in Rm, this works in any dimension, and you compute the output. Usually it's something algebraic, you can really check on this. And of course, his theorem is also about only Gaussians. If it is non-degenerate, really the optimal is achieved only on Gaussians. Otherwise, it's asymptotically achieved by Gaussians. But the problem, we said, okay, now we just have to plug this into the quantum setting. The problem is that a key argument in this proof is the multiplicativity of the norms of the channels, which is also known to be false, but for general channels, as I told you. Maybe for Gaussian channels is true. Actually, this is equivalent to many of these conjectures. So this multiplicativity, we cannot achieve it, so we put some conjectures. So the first conjecture is the analog of his result, Lieb's result, but for this convolution, this is called the attenuator, the convolution with a Gaussian. It's not a general Gaussian kernel, but it's something already interesting and challenging. So the conjecture that we put forward is that if you take any n and any lambda, recall, is the parameter of this mirror, the reflectivity index of this mirror, any energy E, and any PQ norms. So if you look at the norm of this kernel, which is just a tensor product of the single attenuator, because you can always take tensor products. The problem is that the norm will be in general not the tensor product of the norms. Well, the norm is, you can compute it on the Gaussians. Actually, what Gaussians? The thermal Gaussians. This is a special case, but we expect it to be true. And actually, you can reduce to the one-dimensional case. Essentially, this conjecture tells you where the norm should be achieved, and that is also multiplicative, which is false in general. But for this case, it should be true. So why we put forward this conjecture? Because it is partially proved, for example, for any n, and p equal 1, and any q. This was a result by Luciano Mari, Giovannetti, and Holevo. And then Frank and Lieb recently, I think last year or this year, they put forward a proof for the case p equal q and any n. So if you really do look at the norm from 1 to p or norm from p to p, this is true. So it's general to expect that for any n, pq should be true. What we proved instead was the case of n equals 1. And then any pq and energy equals 0. So this is the so-called the dilation. Actually, our proof, I think it can be it's just a matter of really do the computation, can be put forward for any energy greater than 0. The problem is that we are on n equal 1. It's quite difficult to move. I told you these things do not tensorize easily. So if you proved it for n equal 1, you don't have for example, log Sobolev. You can prove it for for one dimension, then you tensorize. But this is not the case in this. So this is the yellow conjecture, and if you do the limit for the norm of p and q that goes to 1, these are kernels, so when p equal q equal 1, you get an identity. But if you take the derivative, you end up with entropies, and there is this nice result, which is called the constraint minimum output entropy, which is really the same, but for entropies. And recall that entropies have a change of sign, so instead of, so you reverse essentially the inequality. So we state that for any n, if you take a state on the tensor product of these bosonic spaces, and you take the thermal state which has the same entropy, if you take the tensor product, then the entropy of the output of this operation, of this kernel, of this channel, is always larger than the one of the in the thermal state. And you can also actually compute. This is really a bound that can be made precise. Also, here the problem is the same. Essentially, we can do a proof for n equal 1, and we don't know anything about larger n's, because they don't tensorize these things. And the problem is also solved in another special case, which corresponds to the case p equal 1 and any q, which is if you don't put this constraint in the input, you can prove that the output is always the optimizer is always the vacuum state, the first eigenvector of the number operator. Okay, now let me move only to the red conjecture, because this is thing where I think where maybe some optimal transport may enter. I don't know. The problem is related about the sharp Young's inequality. As far as I understand, oops, sorry, there's an inequality missing in the first equation here. So what is the Sharpe-Young inequality? You just look at the norm of the convolution between two functions, the R norm, given the norms P and Q of the inputs. Well, it is known, it was known since Braskamp and Lieb and Beckner, I think around the same year, that the norm can be computed on Gaussian functions. And actually recall that the norm is finite, this was already known by Young, this condition 1 over P plus 1 over Q equals 1 plus 1 over R must hold. So the original proof of Beckner, well, there are actually different proofs. Let's say about the proof by Braskamp and Lieb use rearrangements and then some clever way to move from dimension 1 to dimension n. And similar ideas, but more in the optimal transport, I would say, stream, were used by Barth when he proved also a converse inequality in some cases. Then there are other proofs which I would call via semi-groups. So there is a proof by Toscani, and there's also a generalization of this type of inequalities by the fourth authors, Bennett, Carberry, Christ, and Tau. Of course, now the Sharpe-Young inequality is something that we can conjecture, and this is what we did, nothing more than conjecture, in something we call quantum Sharpe-Young's inequality for the beam splitter. We have an analog of this operation of sum, so it's quite natural to say, okay, for any n, p, q, r, and lambda, we just do the norm of the output of this operation, but you take the operation on n modes, not only one. But this is also open for n equals 1, so could be already an achievement for n equal 1. And you fix the norms of the input, then the supremum actually can be restricted to thermal Gaussians. Of course, you have to let the input and output, the two energies vary in general, because the P and Q may be different. And this is something interesting. So it's not difficult to check that the supremum, this quantity is finite. Of course, we don't have the optimal, no, this supremum, not only this one. The supremum is finite, and then we conjecture is achieved by some thermal states if the equality in Young inequality becomes this inequality here, 1 over P plus 1 over Q greater than 1 plus 1 over R. Now the point is here is that the quantum norms, as I told you, the LP norm is this trace, they behave like in discrete space, like in little LP spaces. So if you have the norm of the operator is finite for this choice, you have also for the larger norms of the input. Okay. Instead, for equality, it should be still finite, and then if you have the converse inequality, it should be plus infinity. This we never checked in details, but it's quite reasonable. Okay, now finally, if you take the derivative as P and Q and R goes to 1, you have another inequality, which is the so-called entropy power inequality. And actually, this is the way you can prove. For example, this is Lieb's proof of this well-known inequality. Well-known because it was originally conjectured by Shannon himself. And he gave a proof which was not correct. Essentially, he just checked that Gaussians are critical points. Okay, or actually, the inequality becomes equality if you have Gaussians. Now, the actual proof, so this is a Sharpe inequality for Gaussians, tells you that the entropy of the convolution, if you take the exponential, you normalize in this way, is larger than the same expression. This is called entropy power of the two terms. Now, just to make a connection with what was with the talk of this morning, if you specify this with Gaussian inequalities, since the entropy of a Gaussian is the logarithm of the determinant of the covariance matrix, here you end up with the Brun-Minkowski inequality for matrices. What was called this morning something that God gave us, right, in the talk. And this is another way to prove that inequality, or if you want, you can go so the other way. Now, the interesting thing is that although, okay, as I told you, this could be a consequence of the red conjecture, the Sharpe-Young inequality, actually, the quantum version of this is proved essentially by changing the original, not the Leibniz proof, but there's another proof via heat semigroup. As usually in these arguments, there's many proofs, and this one you evolve with the heat semigroup. You can prove it. It's not simple, but there is the analog. The problem is that this is not the sharp inequality. And let me conclude with the real inequality, which is if you really do the limit in the quantum sharp Young inequality, you obtain another conjecture, essentially, which states that if you do the entropy of the sum of this beam splitter of the two states, well, it's always larger than the same result if you limit yourself to Gaussians, which the same entropies as the inputs. This is something called entropy photon number inequality, and the state of art now is this is completely open, I would say, if the rho A and rho B are general. If one of them is Gaussian, you can, it's one of the previous partially proved results. Okay, so I think we can stop here. The problem is that the ideas from proofs, unfortunately, do not use optimal transport. So I don't want you to spoil you, because these proofs are very ad hoc for the moment, and it would be nice to have new ideas. So if I tell you these ideas, maybe I influence you about possible other ideas. I don't know. So please, if you have any ideas about, for example, applications of optimal transport to prove Young inequality, I would be very interested in this. Also directly multi-dimensions, it would be very interesting. Otherwise, the techniques are very limited to this partial case, but it's a hot area, and there's a lot of competitions also between physicists on this. So if that would be an achievement for mathematicians if you were able to arrive before them. Okay, thank you very much.
Thank you, Dario. Any question?
Okay. Well, you know where I am. It's okay.
Thank you again.
Thank you. Thank you.
So let us close this session and see you tomorrow morning.